Welcome back. Thank you for your patience. So we are getting started now. Let me just remind you the flowing program of the day. With this music below. So we are going to have the program of the next two talks. So Irene and Dima. After which, basically behind you, there will be lunch and drinks and everything. There will be a small banquet, basically, because we're combining two meals into one. And a lot of time for discussions, and you're very welcome to take a stroll in the botanical garden. So you can get your food there. Don't bring your food around, just have the meals there. But then if you want to go for a walk, get some fresh air, that's absolutely fine. You can walk around those gardens that you walk through. Then we are going to have Stanislav's talk here. Of course, it's a much smaller venue, unfortunately. So we will all fit, and some of the many students that wanted to attend will also fit. The other will unfortunately only be able to attend online. But so this is the plan for the poster session. Of course, now we cannot really arrange it. We don't have essentially we don't have support to show your posters. So what we will do is to have the poster session tomorrow. We already had made plans to show the posters in the place where we have the meals and the coffee breaks from tomorrow on. But maybe we will try to find a little bit more time to make it, give you a little bit more time to discuss the posters, since this afternoon was a little bit lost. Okay. I'm waiting for a sign from the technicians that we can start. It's a maybe.
The name is
Irene Valenzuela. Are there any questions in the meantime, like practical things? Maybe, yes?
What time is it?
3:30. Other thing, there were two people that were not on the list this morning when it was the moment to sign. During the lunch break, can they come and find me? These two people, they know, who you are. Yes, one, and the other, I don't see. There you go. So come and find me during the lunch break. And finally, without further ado, Irene.
Okay, thank you. Can you hear me? Okay, thank you very much. Thank you for the organizers for the invitation to give the talk, and especially for putting this cost action into action. And thank you everyone else for staying here despite your empty stomachs. So this might be hard, but I will do my best to capture your attention. And I guess that since we will have a Spanish lunch, like at a late time, what could be best than having a Spanish speaker to entertain you meanwhile? And since we had this beautiful path, this road through this botanical garden, what could be best than following this road towards Precision Swampland? So what I'm planning to do, I'm going to focus on one concrete idea of the swampland and some of these developments that try to make this much more precise and get some useful phenomenological constraints. But first of all, since this is supposed to be a vision talk and it's supposed to be aimed, what we were saying, like for a PhD student that is in your institution but maybe not in your group, that was the instruction. Let me briefly remind you what is the goal of the program and what we are trying to do. So the question we are trying to answer is, what is the space of effective field theories that are weakly coupled to Einstein gravity and can be consistently UV completed, okay? So the message is that if you have some effective field theory coupled to gravity and you have a bunch of higher derivative corrections, not everything that you put here necessarily is guaranteed to have a UV completion, okay? I mean, this already happens in quantum field theory, but in gravity with more reason. So we try to understand what are the rules of the game, okay? So what can go here, and also what is this cutoff? Because depending on what you put here, what we learn from string theory is that this cutoff can actually be lower than the Planck scale. Okay, so this is just my favorite picture. Well, actually, this is my favorite picture. So the idea is that not everything can be UV completed, so the theories that arise from some quantum gravity description at higher energies belong to the landscape, and the ones that are not consistent belong to the swampland, okay? So the swampland are those that cannot be UV completed. Okay, so the goal is to understand what are these constraints, what distinguishes this beautiful landscape from this ugly swampland. And by doing that, I mean, of course, that's interesting by itself because it's like uncovering what are these quantum gravity rules, no, these principles. But the hope is that they can also bring a new way to connect with our universe by providing guiding principles to construct beyond standard models, particle physics and cosmology, and hopefully shed some light also in some naturalness issues, because gravity is different than the other interactions and can induce some UV-IR mixing. So the take-home message is that even if the Planck scale is very high, working in quantum gravity is not just a mere theoretical exercise. It can have implications and can impose non-trivial constraints at low energies. Now, how useful are these particular constraints for our universe is yet to be seen. That's what we are working on. But we have proof of principles that they exist. Like there are at least some constraints that you can see is more or less useful for the universe, but not everything goes, okay? Not everything is consistent. So we have some proposals for these constraints. They go typically under the name of swampland conjectures because they are motivated by what we know from string theory and arguments of black hole physics. But formulating the conjecture is just the first step, okay? So the way we work is that, okay, you identify some pattern using all the data that has been collected in all these years of learning about string theory, and then you have to work harder. You have to provide quantitative evidence in string theory, so this is a fantastic theoretical framework to test it. And then if you want to understand, you want to distinguish model-dependent features from universal ones, you need to understand why these constraints should be true. Like what goes wrong if you don't satisfy it? You can try to do it thinking of black hole physics. You can try to prove it using IDS-CFT, for instance, maybe scattering amplitudes, and so forth, okay? And then you can think of the phenomenological implications. So this is this road towards precision swampland that we are pursuing. So there has already been several years that there has been this growth of activity in this program. So what has been the history so far? So there were some constraints like proposed years ago, which are like the core of the swampland program. Then probably you saw in the archive many more constraints arising at the beginning. After that, what happened is that we started to realize that all these constraints are different phases of the same principles. They are actually related. So right now, there are like three groups, like three basic constraints, which some of them are related to the absence of global symmetries. Others put constraint on the field spectra and constraints on the scalar potential and the landscape of flash vacua. And now what we are entering is in what I call like an era of precision, mimicking cosmology, in the sense that we are really making very precise all these constraints and even giving proofs in certain setups. Okay? So in order to exemplify this, I'm not going to go through all this. I'm going to focus on one. Okay? We want to focus on one idea. So I'm going to focus on this distance conjecture. Why? Well, First, because it plays a central role in the Swampland program because of many of the connections. It's also one of the most natural features from string theory. Like if I had to pick one, I would actually pick this one. You will see why. But it also has phenomenological implications. So it's a bit of a sweet spot between getting something that seems to be universal in string theory, but can have an impact. So, and it's also a very good example to understand how it has changed a lot our understanding of this conjecture in recent years. So there has been a lot of work sharpening the conjecture, getting rid of all the ambiguities, fixing all these order one factors, everything, and even trying to provide proofs that are model independent, for instance, in the context of ADS-CFT. So what I want to do is mainly to focus on this part of ADS-CFT. Okay? Very good. So let me start by summarizing, like reviewing what this conjecture is about. So the idea is that if you have an effective field theory that is weakly coupled to Einstein gravity with some field space that is parameterized by the vacuum expectation values of the different scalar fields. Okay, so you have a theory, different scalars. That happens very often, right? In string compactifications, we get a lot of scalars parameterizing the internal dimensions. But okay, more generally, you get these scalars, and you can define some field space, so such that the metric is the field metric of the kinetic term of these scalars. Okay. What the distance conjecture says is that there should be a new physics, an infinite tower of states that become exponentially light when approaching an infinite distance boundary of this field space measured by this metric. Okay? So, what do I mean? So if you think of this field space, so each point is a different value for the scalar Bev. And you approach some of these boundaries of the field space, you should get this tower of states that become light. And all of them become light. Okay? So you had infinite new degrees of freedom at the boundary. Okay? Good. Now, this happens all the time in string compactifications. For instance, if this scalar happens to parameterize the volume of some circle or some internal space, if you make it very large and go to infinite distance, you're going to get the Kaluza-Klein tower becoming light. That also happens if you go the other way around, like to make them small. That's also at infinite distance in this metric. And then you get winding modes, wrapping brains, and so on. Also, like couplings, like you get the string coupling. You send it to 0, it's at infinite distance, you get the string modes. Okay? So the point is that from the perspective of the effective field theory, getting this infinite tower of states implies a drastic breakdown. Okay? Like you get this new, I mean, you cannot have a quantum field theory description anymore because you have this infinite tower. And then the scale at which quantum gravity becomes important becomes parametrically below the Planck scale, okay? Because they are all becoming massless. Okay? So with this tower, you get also that the cutoff goes to 0. In these examples, like for instance, like you have the string tower, then I'm talking about the string scale. If I have a Kaluza-Klein tower, I'm talking about the Planck scale of the higher dimensional theory, and so on and so forth. Okay? So if you are interested, if you work in particle physics and cosmology, and you have some effective field theory, and you wonder what is the scale at which quantum gravity should matter, it's not true that that's always the Planck scale. In fact, that can happen in the middle of the moduli space, but as you approach these boundaries, this scale is always much lower. Okay? That's what we observe from string theory. So what is this useful for? Well, first of all, it puts a bound on the scalar field range, because I mean, if you are moving in this field space, at some point you find the tower. So this is the maximum field range, the geodesic field range, that you can describe for an effective field theory with a fixed cutoff. But you can go beyond that, because like in general, when we have the effective field theory, all the couplings and masses are parameterized by vacuum expectation values of the scalar fields. So you can also put bounds not only on the value of the scalar fields, but directly on the value of the parameters of the EFT. For example, if you take a weak coupling limit, like a gauge coupling goes to 0, becomes very small, or you try to engineer some approximate global symmetry, these limits are at infinite distance in this field space. Okay? So that means that whenever you try, for instance, to have a very small value of the Gibbs coupling, you are going to find these towers of states becoming light. And then you can use it to put a bound on how small the Gibbs couplings can be. Okay? That's kind of the idea. And that's what we are trying to quantify, okay? Exactly how this behaves. And then, yeah, as I said, like, then you can use it to construct models of like weakly coupled, dark matter, dark photons, things like that. Okay, so as I said, like, this is, I mean, the existence of these towers is kind of one of the most universal features of string theory. You always get these towers when you go to the boundaries. They are behind all these famous string dualities that we know and love. It's very natural. It's not surprising from the perspective of string theory. Sometimes it's like, okay, why you even talk about this? I know this happens all the time. But the key point is that even if it's very natural for string theory, it's very surprising from an EFT perspective. Because you are telling, for instance, that if you have a quantum field theory with a perturbative weak gauge theory, like the gauge coupling is very small, something has to go wrong because you are getting too close to these boundaries and you get this tower of states. And that's something that will never happen in quantum field theory. It's rather the opposite. Like the smaller the gauge coupling, the more control we have of the theory, right? So quantum gravity is changing this, okay? And that's a message that matters when you work for phenomenology, no? Like, and you try to make these couplings very small. You have to be careful that they are not too small to make the quantum gravity cutoff to go down. Okay? Now, so that's the observation. So what we want to do? Well, first, we want to understand why. Like, okay, this is what you observe in many examples, but why do we always get these towers? Can we uncover the quantum gravity principle behind the existence of these towers? Why it has to be wrong? No? And second, we want to make it more precise. We want to understand what is the possible nature of the towers and what is the value of the exponential rate. So exactly how fast they become light in order to be able to give a quantitative prediction for phenomenology. Like, so far it's just qualitative, like they become light, but if you cannot tell exactly how, you cannot give any useful constraint. Okay? So as I said, like the first step was just to identify the pattern, but then, since then, you have to be able to answer these questions. And there has been a lot of activity trying to sharpen this conjecture, understanding the value of the exponential rate and all these things from the perspective of string theory compactifications. But also, there has been recent progress on trying to understand, using black holes and ADS-CFT, why the towers are there. Okay? So what I'm going to do is just, I'm going to give you one slide to summarize what is the state of the art here, what are the values of the exponential rate, and then I will spend the rest of the time in explaining how this works in ADS-CFT. Okay? Good. So, one slide. So, yeah, there has been many papers. I mean, it's impossible to put all the references, but basically, even if you take, the conclusion is that doesn't matter what infinite distance limit you take, you can take very complicated internal manifolds where you have many scalars, go to very different regimes, strongly coupled, weakly coupled, whatever. In the end, you can always find a change of dualities such that the tower of states looks like a Kaluza-Klein tower in some dual frame or some string tower, like oscillator modes of the string. So in the end, it's like coming from string theory, no? Like either the extra dimensions or the perturbative string. Not like wrapping brains, they are never like the leading tower. Okay? So, and then, even more importantly, like the nature of the tower, the microscopic nature of the tower, fixes completely the value of the exponential rate. So depending on what is the nature, you are going to have that the exponential rate is given by 1 over the square root of d minus 2, where d is the dimension of the space-time, if it's a string, the critical string. Or this is, for example, the case in which you just have compactification, in which warping effects are not very important, otherwise this gets modified. Okay? But the basic point is that there is a one-to-one correspondence between this value of the exponential rate and the nature of the tower. And since the Kaluza-Klein tower seems to always decay faster than the string, because it's more dense, there is a sharp bound on the value of the exponential rate, which is what you need to give a bound on the field range. Okay? So this is the state of the art right now. And what I want to do the rest of the talk is to understand how, if so, this gets modified in ADS, and whether we can prove this using CFT. Okay? So it's not just a matter of checking example, but we have a general proof of this conjecture. And well, just you will see that actually this has to be modified because we can have more types of tensionless strings. We'll see. Okay, so how do we translate this constraint to ADS-CFT? Well, let's start with the easiest example in which we really have a moduli space, so all the scalars are massless. And this translates, moving in this moduli space is equivalent to moving in the conformal manifold of the CFT, which is the space of exactly marginal couplings. The field metric of the kinetic term that we use to measure the distance maps to the Samolov-Hikov metric in the CFT, which is given by the two-point function of the marginal operators. And then this tower of light states are going to correspond to tower of operators that are close to saturate the unitarity bound. So the distance conjecture translates to the statement that there should be an infinite tower of operators saturating the unitarity bound at every infinite distance limit in the Samolov-Hikov metric, such that the anomalous conformal dimension decays exponentially in terms of the distance measured by this metric. Okay? Good. So does this happen? And if so, what are the towers? What is the microscopic nature of this tower of operators? Well, the answer depends on what dimension you are. So this is something interesting in ADS-CFT. It seems to happen that if you are in two-dimensional CFTs, all the examples that are known and has been conjectured that is the only option is that you have the scalar gap going to zero. So you have like tower of scalar modes that in the bulk correspond to tower of Kaluza-Klein states and so on, like partial decompactification. While in dimension bigger or equal than 3, all these towers always correspond to higher spin modes. Okay? So like string states in the bulk. And this is what we call the CFT distance conjecture, okay? Including this separation between this nature of the tower. Now, if you want to prove this, okay, that this always happens, you need to show this one-to-one correspondence between the infinite distance and the infinite tower. This is supported in all the examples in holography, but recently, after we've put this conjecture, like just in these 2 years, there are already 2 papers proving this direction of the arrow, so that once you have either the higher spin gap in higher dimensions or the scalar gap going to 0 in 2 dimensions, this point must be at infinite distance in field space. And now there is work also trying to prove the other one. So this is one example in which this constraint is not out of reach to try to give a rigorous proof. And actually, the techniques employed here are not like new techniques that we had to develop. It's just using known techniques to address the question that is interesting for us here. Okay? So I hope this also encourages try more using your own techniques to prove some of these statements. Okay, so how much time do I have? 20 minutes? 5, 7? Okay, so in the last 5 minutes, let me focus on the case of the higher spin modes and give you a bit more details of why they appear, like how this is working. And also to, as I said, like to sharpen, to understand how light, what is the exact rate at which they become light, and what can we learn from it. Okay? So, very quickly, so let me focus on dimension bigger than 2. The only conformal manifolds that are non-compact, that are known in CFTs, occur in 4 dimensions. Okay? Although there is this proposal in 3 dimensions that would be nice to study more. But let me, for the moment, focus in these four-dimensional superconformal field theories to explain you a little bit like what is the intuition of how you get this tower of operators of higher spin modes. So in all these examples, the infinite distance limits are weak coupling limits in the CFT. So you have some gauge coupling from your CFT that goes to 0, which means that at the boundary, at the infinite distance limit, you get this, like a part of the theory becomes free. Okay? And now you can see what's going on. Once you get a free point, a free sector, by Maldacena-Syboderov, this automatically implies that you have a higher spin symmetry. Okay, so there's a one-to-one correspondence between having these weak coupling limits and a tower of higher spin operators saturating the unitarity bound. But okay, to prove the distance conjecture, it's not enough to show the existence of the tower. You need to show that they decay exponentially. So you can do that. You can say, okay, if you take the free limit, the gauge coupling goes to 0. You know that by perturbation theory, the marginal operator is just the trace of f squared. You can compute what is the Samologikov metric. And it always takes this hyperbolic form, such that in the end, the anomalous conformal dimension behaves exponentially in terms of the distance. And you can compute explicitly what is the exponential rate, like how fast it goes to 0. So this implies that from the perspective of the ADS dual, you are going to have a tower of higher spin fields with an exponential rate, which you can compute to be the square root of 2 times the central charge over the dimension of the gauge group that is getting free. Okay, so you see that the exponential rate gives you a notion of what is the portion of the theory that gets free. Okay? And moreover, it's also there's a lower bound, which is consistent with the lower bound that I gave you before. Okay? Okay, so one last comment is not only, I mean, this is a way to sharpen the conjecture. This is the concrete value that you have for these exponential rates. But it's not only that it's lower bounded, like the numerical values that this can have are also very constrained. So to give you one example, you can take the full classification of 4-dimensional superconformal field theories that have a simple factor for the gauge group, okay, just to simplify a bit the story, so just everything gets free, okay, you just have one factor, one gauge coupling. So these classifications were performed in these papers, and then you compute this value of the exponential rate, and you get that there are only 3 possible values that arise. That's it, for all these superconformal field theories. And they are mixed. It's not that they correspond to the different gauge groups, they get mixed. And it's not that they correspond to n equals 1 or n equals 2, they also get mixed. It's like you have a new classification of the superconformal field theories in these 3 groups. Okay? Now, you can ask, okay, why this is happening? Well, if you study this in more detail, you can see that in this case, you can write this exponential rate as a function of the ratio of A over C, the 2 central charges of the CFT. And in all these cases, it happened, I don't know if any of you knew before, I didn't know, that A over C can only have 3 values. You can show this just because of having the CFT, okay, the conformal manifold. So, and this is what gives rise to these 3 values of the exponential rate. Now, I told you before that the nature of the tower completely specifies the value of the exponential rate. So now you can ask, okay, why you have 3 values here? Like in all these cases, they are all towers of higher spin fields. Okay, so it's like having a tensionless string limit in the bulk. So does this mean that these 3 values correspond to 3 types of tensionless strings? Like these 3 types of quantum gravity resolutions that we can have? And the answer, I mean, we think is yes. So this is work in collaboration with Jose Calderón Infante. We are computing, for instance, the density of the operators, like the Hagedorn spectrum at the free limit. So indeed, one can see that there is a Hagedorn growth because of having this tensionless string. But the Hagedorn temperature is different for these 3 cases. Okay, so they really suggest that there are 3 types of tensionless strings. The first one is the usual critical string. So this is like the string in n equals 4 superjump Mills. So any holographic theory that has A over C equals to 1 to Lie in order it's gonna, like the free limit always corresponds to this, our known critical string. But it seems that there are two others, which happen in non-holographic theories in the sense that even if you have a large n, you don't have a large gap. Okay, so A is different from C. And they correspond to different string worksheet descriptions that you get at infinite distance. Okay? So first thing you learn is that this distance conjecture seems to be more general than only for like weakly coupled Einstein gravity descriptions. It works for all CFTs, regardless of whether you have a large gap or not. So it's a very intrinsic feature. And second, by understanding these limits, we get information about the possible quantum gravity resolutions, no? Like what's going on at high energies, what are the string theories that appear. And since there are only these three groups, it also means that there should be a way to, some duality or some way to connect them among each other, okay? Like the CFTs that are in these groups. Okay, so I think this was it. I had some bonus slides, but I don't know if I have time to explain it. I should go to the conclusion. So you can ask me later about it, okay? It was just in case I had time. It's just to show you, just so you know what's about. The idea is that if you try to understand what happens beyond the conformal manifold, so when the scalar fields get also mass, you can actually use these values that I told you of the exponential rate to give an argument against scale separation in ADS. Okay, and to explain why you don't have scale separation. But then you can ask later. So let me conclude. So yeah, I think the message is that consistency with quantum gravity at high energies can have implications, like not everything goes. We are trying to make all these Swampland constraints more precise, giving sharp bounds on the value of the exponential rate, classifying all the possibilities, and trying to give proofs, at least within concrete setups, like ADS-CFT or classes of string compactifications. So let me finish with the message that, I mean, this is just one example. There has been also more recent papers using ADS-CFT or CFT techniques in general to prove like the good gravity conjecture or other Swampland constraints. And there is much more than can be done. Okay? So I hope this encourages everyone to use your favorite approach to quantum gravity to try to relate to some of these constraints to see if you can understand what's behind and see if we can all together uncover what is the quantum gravity constraints that are imposed at low energies. So thank you.
Thank you very much. Questions? Okay, several at the same time. Let's go.
Hi. So in the context of Minkowski vacua from Calabi-Yau compactifications, there are these so-called K points at infinite distance, which don't have, as far as I know, a good geometric understanding. Are you saying that it's
Which
still...
one? Sorry, say again?
So that is so-called K points at infinite distance, corresponding to variations of Hot structures where, where the monodromy at infinity is not maximally unipotent, so they don't correspond to large volume limit.
Yeah.
But I'm not sure it's known to what is their...
Yeah.
So can you actually prove this distance conjecture in that context?
Yeah, we had a paper, like actually one of the first ones, in which we took exactly, like tried to get, the complex structure of a Calabi-Yau threefold, classify all possible infinite distance limits, which are classified by the the order of the infinite order monodromy, like the nilpotent orbit theorem. And then we use techniques of Mises structures to prove the existence of the tower of BP states.
But still, there is no dual frame in which they would just be your Kaluza.
Yeah, so in that case, exactly. So in that case, we can show, using the Hodge theory, we can show the existence of the tower of states. But it's an open question to understand, what is the duality, right? Like, what is the change of dualities that would show that they are Kaluza-Klein or string Mossos? That's still an open question. So we know the tower is there, we know the exponential rate, and knowing the exponential rate gives you information about what they should correspond to. So you can see that they correspond to, like, they have the same exponential rate that a Kaluza-Klein tower of different dimensions would have. But it would be nice then to follow to try to uncover the chain of dualities that make that manifest. That's open. Yeah, no, that's super interesting. Yeah, indeed.
Can you expand more on the non-critical strings? Are these supersymmetric theories? Do you know the full spectrum?
Yeah, so these are all superconformal field theories, so with n equals 1 or n equals 2 in 4 dimensions. Well, and n equals 4. Like all the ones that have, I mean, what I show you here are the ones that have just one simple gauge factor, so there's just one gauge coupling and one limit to make it simple. And in some cases, like for instance, to give you one example, so one characteristic example of one of these theories that has like one of these non-critical string is n equals 2 super QCD with nf equals 2n flavors. Second? So in that case, I mentioned this example because in that case, there are very nice papers by Eli Pomoni, Leonardo Rastelli, and so on, in which they try to understand the bulk dual. And the critical string, like the non-critical string, is a combination of, so you get both the fundamental string and also some DC branes becoming light at the same rate. So it's kind of a combination, like in the end what you get of these two, that are like non-critical. They also try to describe them as non-critical closed strings in a bulk which is not completely geometric. And there are some dimensions which are non-geometric. So this is one of the examples. The other one, I'm not sure yet. Like I'm trying to investigate better what should correspond to. But yeah, I don't have such a clear picture yet. But that's what we are trying to understand now. OK, what are these? And especially we know where they should appear because of this exponential rate. So yeah, can we understand the bulk dual of any of them or connect them to each other? Yeah.
Yes, a more philosophical question. So when you say that you're finding constraints on quantum gravity, are these constraints do not seem to be based on general principles of physics, but more on specific predictions of string theory. So imagine, for example, let's imagine, for the sake of the argument, that the right theory of quantum gravity is loop quantum gravity. So are these constraints to be still true or not?
That's part of the program to understand, right? So here I focus on this, which really comes from string theory. It also has some arguments thinking of black hole physics now. So let me say, if it only comes from string theory, then we will always say that it's part of the string swampland. We don't know if it's a general feature of quantum gravity or not. The reason why we say, OK, we think there are constraints from quantum gravity is because sometimes you can give more general arguments independently of string theory. Like, for instance, the typical example is with no global symmetries. Like, you also have a lot of evidence from string theory, but you also have arguments just based on black hole physics that suggest that it's something more general. Whether it works in other approaches of quantum gravity, I think that has to be seen. Typically, it's not possible, like they are not explored so quantitatively to be able to check them. And I think, honestly, I think both options are fine. Either we realize that maybe they are completely general because they come from black hole physics and other more general principles that we think should apply generally, or maybe some of them are more specific to string theory and can help to distinguish string theory from other quantum gravity theories if they exist. So that's part of the program itself. And depending which one, there is more evidence for one or the other option.
One last question for Irene. I don't see any, so let's thank her again. Thank you very much. And we are almost ready to welcome the last speaker for the day, before, of course, the public talk. That is Dima Sorokin, who is getting mic'd up. And I remind you, after this, basically through those doors, you can go and get your well-deserved food. But try not to eat your neighbor while you listen to Dima's talk. All right, please, Dima.
Do you hear? Yes, I hear myself as well. So, Okay, an excuse for choosing this topic of nonlinear electrodynamics is the fact that these models celebrate their 90th anniversary in this period, and the topic starts from the famous Born-Infield electrodynamics proposed in 33-34, and it remains basically the most famous theory because as we all know, it has a lot of important applications in string theory. Another electrodynamics of nonlinear electrodynamics is the Euler-Heisenberg effective theory proposed in 35, which is the most phenomenologically related to fundamental interactions which we observe, theory which describes the quantum electrodynamics in an effective way when matter fields like fermions or some charged scalars, if they are present, get integrated. But during these 90 years, people proposed a huge number of models which come with some strange names like logarithmic, double logarithmic, exponential, rational, and others. And they were proposed in different contexts and for different purposes. And basically, nonlinear electrodynamics is an area which is applied in several directions of research. For example, these kind of models have been used to consider some black hole solutions, in particular looking for regular black hole solutions in Einstein theory and beyond. Then these models of nonlinear electrodynamics were also used to, for example, resolve the Big Bang singularity or describe inflation and dark energy. And also in the area of condensed matter theory and optics, it has many applications, including the description via the ADS condensed matter theory correspondence. And the latest example of these theories was found quite recently by Igor Bandas, Kurt Lechner, Paul Townsend, and myself. And it's a curious example because we were working on a completely different problem. Well, maybe not completely different. We were studying a tensionless limit of M5 brane of M theory. But then Kurt Lechner came with some very simple but question: what is the theory which, like Maxwell theory, would be conformal invariant and duality invariant simultaneously, but would be non-linear? It's quite surprising that this question was not asked during all these years of the development of the theories. And it turns out that there is a unique theory of this kind which modifies Maxwell theory and still remains electromagnetic invariant under electromagnetic duality and is conformal, classically at least. So in this talk, I would like to review some basic features of Ned's theories and concentrating on Mach theories. We'll discuss some of its solution and implications, and especially in the context of new TT-bar-like deformations of field theories with stress energy tensors. So let me start with the definition. What is the nonlinear electrodynamics? It's a theory which generalized Maxwell theory to a theory of self-interactions of electromagnetic fields. So the generic Lagrangian depends on the two possible invariants in 4 dimensions, which one can construct from the field strength of the electromagnetic field. This is a scalar and a pseudoscalar, where phi tilde is the Hodge dual of F. And usually we require that in the weak field limit, these theories reduce basically to Maxwell theory plus some higher order corrections. But as we'll see, it's not always it does not happen always. For example, in the mod-max case, because it's conformal theory, there is no weak field limit, but the theory reduces to Maxwell theory in the zero limit of its parameter. Let me give an example of the Heisenberg-Eller theory, which, as I said, the most close to phenomenological applications. So in the Heisenberg-Eller theory, these coefficients are very small. As you can see, the B is related to A in this way, and A is constructed from the fundamental constants of electrodynamics, so the Planck constant, the fine structure constant, the mass of electron, the speed of light, and so on. And the value of A is 4 × 10⁻25 of Tesla in the units of magnetic field. So the effects, quantum effects of non-quantum electrodynamics are really small. And only recently in CERN, several years ago, this CERN has managed to measure, for example, the photon-photon scattering, which is in agreement with the value of these constants. Now, what we would like to have in this nonlinear electrodynamic theory, what kind of properties we would like that these theories have. And the first is, of course, the consistency of the theory, for example, causality and unitarity, which restricts the form of this Lagrangian. There has been activity on finding the conditions of the Lagrangian, for the theory to be, for example, causal, and in very recent work by Jorge Russo and Paul Townsend, they have found the most general conditions which the theory should satisfy for strong causality. And the basic condition which enters in the definition of these properties is the Hessian, which one constructs as a second derivative of the Lagrangian with respect to the electric field. And the theory is causal basically when this Hessian matrix has all its eigenvalues non-negative. Then one may ask when the theory may be conformal, and this happens if the Lagrangian is a homogeneous function of degree 1 with respect to the rescaling of the electromagnetic field. For example, if we rescale these scalars S with some parameter A, then the Lagrangian should have this form, because then the rescaling with respect of the Lagrangian can be compensated with the rescaling of the coordinates here. And then another important property which we would like to have, for example, which we know that plays an important role, is the electric magnetic duality, which in the case of nonlinear theory has the X as follows. So we have the equations of motion here, which we get from the theory, which in the Maxwell case just reduced to F mu nu here. And then there are Bianchi identities. And then we would like to have the symmetry under which these, the left-hand sides of these equations are rotated by some SO2 matrix, and then we get some new fields phi prime and corresponding Lagrangian, which should have the same form as the initial one. And then we are saying that the theory is invariant under electric and magnetic duality, which imposes this condition on the Lagrangian of the theory first found by Belenitsky-Birula in '83. The famous example is the Born-Infeld theory, whose Lagrangian is, of course, well known, and T is the coupling parameter of dimension of energy density here, and it's associated with the D3 brane tension in string theory. So the important property of the theory is that it is duality symmetric. So its Lagrangian satisfies the duality invariance condition, which I have shown in the previous slides. And this was already noticed by Schrödinger in 1935, but then exemplified by Belinsky-Birula in 1983. And of course, we know that when T goes to infinity, this Lagrangian reduces to Maxwell theory. So what happens if we now require that the theory is, the Lagrangian also satisfies the conformal invariance condition in addition to duality invariance? And then it turns out that there is a unique theory, basically, which is this modified or Maxwell or mod-max theory, and its Lagrangian has the following structure here. So it has the dimensionless parameter gamma, which enters the Lagrangian under the hyperbolic cosine and sine. And the parameter should be greater or equal to 0. When parameter is equal to 0, it's a Maxwell theory. And this, the fact that it is greater to 0 is the causality condition which I discussed earlier. Then, so you see that this theory is basically non-analytic. Here it has this square root, and the energy momentum tensor has this form. It is proportional to Maxwell theory times some scalar factor. The energy is always non-negative, and the trace is equal to 0, which signals that the theory is conformal. So let me show the equations of motion which we have. So there is the linear piece and the nonlinear piece here, and from which we see that there is an ambiguity when S and P both goes to 0, so there is a 0 by 0 ambiguity of this kind. But the vacuum is still a well-defined solution, though, for example, the null fields and the plane waves, which satisfy the conditions that S and P are equal to 0, are not well-defined solutions in the Lagrangian formulation. But it turns out that if you go to the Hamiltonian formulation of the theory, then the plane wave solutions are full-fledged solutions of the theory. Of course, because of the nonlinearity, it's not easy to find solutions of the theory, but at least some simple class of solutions can be easily found. For example, when P and AS are proportional to each other, then these equations simplify and basically become linear. One solution which people intensively studied in these 4 years almost is the effects of this theory on the solutions of Einstein equations, and in particular on black holes. And the simplest example is the Reiser-Nordström solution modified by the mod-max fields. So we have the standard black hole metric ansatz here, and then it turns out that to satisfy the mod-max equations of motion, the Coulomb part, where Q is the electric charge of the black hole and Qm is its magnetic charge. So this is basically the Coulomb potential here, and it is modified by the gamma parameter in this way. And the function Fr has this form, so we see that the extremality condition for this Rieser-Nernst black hole is modified by the e to the minus gamma, the relation between mass of the black hole and the square and their charges. So for increasing gamma, we have a kind of screening effect. One can have less massive black hole here. And people studied more general solutions of this kind, like tau NAT accelerating black holes, Robertson-Trautmann spaces, black hole thermodynamics, and found how the dependence on gamma affects the behavior of this object. One of the open problems which I would like to raise here in this part of the talk is that the rotating black hole solutions have not been found yet. Not only in the MODMAX theory, but in general, there is a kind of abstraction or a problem of finding rotating black hole solutions for a general class of nonlinear electrodynamics, and that might be an interesting, challenging problem to study. Okay, now I think it's time to pass to the second part of my talk, which is related to the TT bar-like deformations in Maxwell's electrodynamics and more general in different theories in various dimensions. So it was triggered by the structure of the MODMAX Lagrangian. And so let me say just a few words about what are TT bar deformations, how they started. So they were put forward by Zamolodchikov in 2004 for deforming two-dimensional quantum field theories and CFTs with the use of some composite irrelevant operator built of the components of the stress energy tensor in such a way that the good properties of the initial theories remain after the deformation of the theory with these irrelevant operators, in particular integrability and other quantum properties of the theory. So the deformation, as it was proposed, it works as follows. We start from some Lagrangian of initial or seed theory and some operator composed of components of the energy momentum tensor, then recompute the energy momentum tensor for this additional deformation, substitute it into the second order, and so on. And then, in the end, the assumption is that this series of deformations closes to some expression, and one gets the so-called flow, TT bar flow equation, which says that the derivative of the final theory we get upon deformation with respect to the deformation parameter is equal to the operator we used at each step to deform the theory. And the most prominent operator which people used in 2 dimensions is 1/4 of the determinant of the of the energy momentum tensor, which is the well-defined operator, local operator in the quantum theory. So that was the main requirement for choosing this form of the deformation. Then, much later, people started to study whether in higher dimensions there are deformations of this kind, and they found that, for example, the Born-Einfeld theory in 4 dimensions can be also treated as a energy momentum deformation of Maxwell theory. So it was found that if you take the Born-Einfeld Lagrangian and take its variation with respect to inverse of the tension parameter, then this derivative is equal to the following combination of the energy momentum tensor of Born-Einfeld theory itself. And it turned out that the MODMAX theory also can be treated as a TT bar-like deformation, but with a different operator, which is irrelevant here, because the operator, so we take the derivative of the Lagrangian with respect to the gamma parameter, and we find that it is equal to this square root of this combination of the components of the energy momentum tensor here. And so this observation triggered the development of so-called root TT bar deformations of theories in different dimensions, and in particular in 2 dimensions. And so let me just show this diagram here, which shows how the Maxwell Lagrangian in 4 dimensions can be deformed, but also the same diagram can be applied in other dimensions, for example, in 2 dimensions or 6 dimensions for getting deformed theories. So if you start with the Maxwell Lagrangian and require that the deformed theory with respect to some parameter satisfies this condition, we find that the resulting theory is the Born-Infield theory. Then we can deform this theory with a this marginal operator and get something which is called mod-max Born-Infield, which I'll show in the next slide. Or we can go in a different way. We can deform first the Maxwell to mod-max using this operator, and then apply the same operator we used for the Born-Infield theory to get the same theory. So the 2 deformations of, in this case, commute and give this new theory, whose Lagrangian has the following form. So in comparison with the standard Born-Infield, where there was this f mu nu squared under the square root, here, instead of f mu nu, we basically have the Lagrangian of mod-max theory. So this is the generalized mod-max Born-Infield theory, which one gets upon the specific TT bar deformation of Maxwell theory with 2 parameters. How much time do I have? Not very much. Okay, let me 5 minutes. Okay, I think I will just skip mentioned briefly. So what has been done in this TT bar business upon noticing that there is a new root TT bar deformation with the marginal operator. So the mod-max theory and its Born-Infield generalization was reduced to 2 dimensions, and people found new theories of scalar fields which can be interpreted as TT bar deformations. An interesting observation recently, which goes beyond mod-max theory, but it concerns all class of nonlinear electrodynamics, is that the TT bar deformations of the theories can be reinterpreted as some coupling of the usual initial theory to gravity. The general discussion of root TT bar deformations has been considered, and then an interesting result was by Borsato, Ferco, and Sfondrini that classical integrable models like principal chiral models or symmetric space sigma models remain integrable even upon the root TT bar deformation. For example, the deformed PCM model has this form with J being the currents of a certain gauge group here. Another interesting observation was that there is a an analog of two-dimensional mod-max-like oscillator, which is exactly solvable theory and fully quantizable theory in, say, one-dimensional mechanical system. There was work on the relation of TT bar deformations in the context of ADS-3CFT2 correspondence and in the context of coupling these models to Jacobi Teitelbaum gravity and others. Recently, we have also considered these TT bar-like deformations, including ModMax-like chiral two-form theory in 6 dimensions, and there are many other directions which I have not had time to mention. So let me conclude just with some open problems. One of the problems is some fundamental origin of say, ModMax theory. We know that nonlinear electrodynamics models should be considered as effective field theories, and only for few of them, like Born-Infeld theory, we know their origin. For example, Born-Infeld is related to string theory, and as I mentioned, Heisenberg-Eller's theory is related to QED. So one may ask what is the fundamental origin of ModMax, and some hint is that this theory might be some theory of Maxwell theory coupled to axionic-like scalar field. So another question which I may ask, is there any interpretation of ModMax and is Born-Infeld generalization in string theory? And this question was addressed by Nastase, for example. Then one may ask whether there are 6-dimensional supersymmetric versions of chiral two-form ModMax theory and Born-Infeld. And the 4-dimensional supersymmetric ModMax theories do exist, which have been constructed some time ago. And another topic of interest is to have a more deep insight into the implications of the TT bar deformations in different dimensions, and in particular root TT bar from the point of view of quantum theory. The standard TT bar deformations are well defined at the quantum level, but the root TT bar deformation is only understood at the classical level, and even in 2 dimensions. Though, as I have mentioned, in 1 dimension there is an example of completely quantizable theory of this anharmonic oscillator. Then one may ask the question if the effective action of ModMax theory have any sensible structure, and there are some preliminary results in the literature about this topic. And then I think the interesting topic is the study of TT bar-like flows or energy momentum deformations of the chiral 4-form gauge theory in 10 dimensions, which may be related to the construction of S-duality invariant high-order corrections to the action of type 2b supergravity. So I will stop here. Thank you very much.
Thank you, Dima. Questions for Dima? Yes.
Just one comment. At the beginning of the talk, you said that you can use nonlinear electrodynamics to support regular black hole solutions.
Yes.
That's ruled out now because any causal theory obeys the strong energy condition. And if the strong energy condition is obeyed, then the singularity theorems by Penrose implies that there must be a singularity. So no causal nonlinear electrodynamics can support a regular black hole solution.
Even for purely magnetic case, or you are talking about electric black holes?
In general.
In general, either electric
causality implies the strong energy condition, and that implies singularity.
That implies that even magnetic
Even
gases
magnetic,
rule
yes.
that. Okay, thank you.
Yes.
So thank you. No, just a comment to Jorge regarding this discussion. So actually, the theory of nonlinear electrodynamics discovered by John Beato and Garcia, I insist that they have a small issue that people overlook, is that the Lagrangian depends on the parameters of the solution. So to say, the Lagrangian depends on the electric charge that you have to introduce in the solution in order to have a regular solution. So therefore, this is the way in which they manage to cook a theory in which they find this regular solution, because actually one can argue that that the parameters of the theory are fine-tuned with the corresponding solution. So this is the way in which they manage to do that. So and then if you want to find regular black holes in the context of nonlinear electrodynamics, as Jorge was saying, in order to break the singularity the singularity theorems of Penrose, then you could go to higher quadratic corrections, and then by including higher quadratic corrections, you can indeed obtain regular black holes. But this was just to clarify Jorge's comment.
Thank you. Any more questions or comments? Yes, one. I'll give you the mic.
Some small question. What about, you told about 2D Modmax oscillator, mechanical system, and told that it is exactly solvable.
Yes.
But is it superintegrable or not? It means that, is it superintegrable system or not? Did you present its constants of motion additional?
Yes, in this sense, I think yes.
In this sense.
It is, yeah.
But spectrum is non-degenerated.
No, as far as I remember.
Okay, thanks.
Okay. I think in view of time, it's time to thank Nim again. So very briefly, through those doors, there is dinner or lunch, whatever you want to call it. Then we come back here 5:30 for the talk of Stanislav. There won't be any external public for reasons of capacity of the room. Unfortunately, it will be us here and people connecting from home. If you want, while after lunch, you can also stroll to the botanical garden. It's also very beautiful. It's the oldest botanical garden in the world. It's more or less 500 years old, almost 500 years old, and it has some very nice plants of historical significance as well, plants that were very old and a curiosity when Goethe was visiting, and he wrote it in his books. So you can take a stroll, and after 4:30, probably you can also visit the museum for free. Before they are doing something there, but after 4:30, it's an orange building. You can just visit and take a stroll there too. So if you want to, stretch your legs after lunch /dinner /apero. For tomorrow, please, the people with the poster, bring your poster in the morning. You will be able to hang them in the new venue, which will be Palazzo della Salute, different place from this and from the previous one. You'll get an email. Okay.
Good afternoon and welcome to the University of Padua. Welcome also to those who are watching us live on the university's YouTube channel and on the Cost Actions YouTube channel. A very warm welcome to Stanislav Smirnov, who is a professor in the section of mathematics at the University of Geneva and a winner of the Fields Medal in 2010. Professor Smirnov's lecture today is, of course, part of the kickoff meeting for the Cost Action Fundamental Challenges in Theoretical Physics. Our first speaker this afternoon is Alessandro Sfondrini, who is the Cost Action Chair and a professor in the Department of Physics and Astronomy.
Thank you very much. I just want to say a very few words to welcome you again and to tell you just a little bit about the Cost Action that was just mentioned. This is a new network funded by the European Union that brings together theoretical physicists and mathematicians, people that work at the interface between physics and mathematics. And of course, Stanislav is an excellent example of this research. So we are very, very happy to have him. We started this network just in October last year, and the network grew very rapidly. It has over 450 members across 50 countries. And our research is very lively, as this first day of this general meeting, our first general meeting has shown. Our activities will continue in the next days. People who are in Padova can come and listen to the talks, or they can just connect to the Cost channel to listen to the talks and learn more about our activities. But of course, the real highlight of tonight is Stanislav's talk. So I would just thank you very much. Hope you to have you tune in our future activities, and please enjoy Stanislav's talk.
Thank you, Professor Sfondrini. Next on the stage is Professor Marco Ferrante, Vice Rector for Teaching and Education.
Hi, welcome everybody, and I'm sorry for the last-minute change that we have made of a room for the seminar, but you have seen that we are experiencing some problems in our rectorate. Okay, I write something to not to forget many things. Okay, it's my great pleasure to be here today in the beautiful botanical garden of the University of Padua, the oldest university scientific garden in the world, founded in 1545, to introduce such a distinguished speaker, Stanislav Smirnov. He graduated with a degree in mathematics in 1992 from St. Petersburg University in Russia. He received his doctorate in mathematics in 1996 from the California Institute of Technology. Between 1996 and 1998, he worked at Yale University, the Institute for Advanced Studies in Princeton, and the Max Planck Institute for Mathematics in Bonn. From 1998 to 2023, Professor Smirnov worked at the Royal Institute of Technology in Stockholm, and in 2023, he became a professor of mathematics at the University of Geneva in Switzerland. Professor Smirnov has primarily focused on percolation theory, where he proved Cardy's formula for critical site percolation on the triangular lattice and deduced conformal invariance. He also established conformal invariance for the two-dimensional critical easing model. This in 2010 at the International Congress of Mathematicians in Hyderabad, India, Professor Smirnov was awarded the Fields Medal, the most prestigious prize for a mathematician, for his work, indeed, on percolation processes and the easy model. The title of today's lecture is Tiles and Puzzles. As in the abstract, let's suppose we have at our disposal in infinite quantities some different tiles, we have here on the whiteboard, or puzzle pieces. Can we tile the entire floor? How many tiles will there be for a given area? Okay, these two questions may seem simple to explain, at least for me, but we will discover that even for simple tessellations, such as those involving two different polygons, these problems become very, very interesting and refer to many areas from logic to statistical physics. Okay, in conclusion, I would like to express my gratitude to Alessandro Sfondrini and all the colleagues who have organized this lecture magistralis, as well as the Department of Physics and Astronomy Galileo Galilei and of Mathematics Studio Levi Civita for their support. I will now stop here and invite Professor Smirnov to take the stage for his talk.
So thank you very much for the introduction. Thank you very much for coming. Before I start, I would like to say three things. One thing, thanks for your hospitality to the University of Padua. And actually, last time I was here was during COVID, so it's much livelier now in many senses. And to Alessandra specifically, what is really impressive how you deal with all these troubles. It's like Swiss efficiency almost, or even more. So bravo. So the second thing, of course, it makes my job slightly less trivial because I was supposed to give a popular talk, and now somehow everyone in this conference probably knows everything I'm going to say, and they were kind of forced to stay. Well, on the positive side, it's a very nice location, Botanical Gardens, it's maybe not as magnum as the Magna Auditoria, but still it's very nice. And then there are popular people, hopefully are by Zoom, and I thought of bringing a bag of chocolates and giving chocolates to people who don't have PhD in math or physics when they answer questions, but since everyone has PhD in math physics, you get at best this chocolate, but we'll still try. And the third thing is that how do I fit in this sort of high energy physics, because that's the main subject of the conference. Bruno today mentioned already Tullio Levi Civita, so it's an example of a mathematician who was actually mostly interested in mathematics, but did very important thing for physics, and that's what we try to do. If you go back at this time, there will be everyone from Minkowski to Hilbert. And you know, like he recounted the story of Einstein. Einstein famously said that there are two good things in Italy, Levi Civita and spaghetti. Now, Einstein was totally wrong. There are many more good things, as we already learned during this conference, and not only in culinary or scientific world, but especially in culinary and scientific world. So I will try to say more on the mathematical side and a little bit touch upon how problems arising from curiosity in mathematics help physicists, how physics problems help mathematicians, and how problems from different areas, they sort of come together. And I will start with a sort of an easy question. Okay, now. It changes two slides. Okay, how do I do so that it changes one slide? Okay, good. So who has seen this picture? Wow. You get a chocolate, Alessandra, you get, well, okay, you get a big chocolate because even though you have PhD in mathematics, you get a big chocolate for organizing the conference. So what does it have to do with Einstein? So it's actually called Einstein, but it's a pen on German words, one stone. So it's a special tile with which you can tile the plane. So this is actually here. You can try after the talk. It's actually a lot of fun trying to tile with this tile the plane. And what you realize fairly fast that you start going on, and sometimes it's easy, sometimes difficult, sometimes you have to go one step back. So you can tile the plane, but there is no way to do it periodically. And it was for a long time an open question whether there is such one tile or whether there is such tile at all. But let's maybe start with this. So my talk will be in 6 parts, each more difficult than the previous one, and on slightly different subjects. So the prelude is, can we tile by a given tile? So let's start with a very simple example. So you assume that you have an infinite box with infinite number of tiles, and then you can get them out, and this tile is very interesting. You can tile so for example, the first question, can you tile the plane periodically with this tile so that there is some period? Okay, I mean, you get a big chocolate if you don't have PhD in math or theoretical physics. But yes. Okay, well, that's too easy. I can still throw some chocolates maybe at you. So it's who said yes? Yeah, that it's okay, you get the chocolate. Wow, good job. So there are both periodic and aperiodic, and for periodic one, you can just add 2 of them, and then you get a rectangle. If you have a rectangle, you can take 4 rectangles to have almost the Swiss flag, but slightly perturbed. And then you can tile by this the whole plane. I mean, there are many ways to tile it periodically. There is also a way to tile it aperiodically. If I move one of the rows some distance irrational to the left, this will destroy at least vertical periodicity, but not the horizontal one. So the question is, can you tile aperiodically so that there is no period? So any ideas how to do that? Unfortunately, people on Zoom don't get chocolates. I'm sorry. I can leave it back in the courtyard of the university, so or I can mail you if you write me an email. But so any suggestions how to do a periodic thing? No. Okay, I will give a hint. So let's try to do this thing. Take 4 figures like that and assemble this figure. So what's in common between these 2 figures? Yeah, that's the same shape. You get a chocolate. Yeah, so it's... Sorry? Well, okay. You get 3 chocolates, yeah, for you and 2 kids. Do you have a wife? Yeah, okay, you get... Oh, okay, you get a chocolate. Yeah, that's... for having a smart husband, yeah. So you see, it's exactly twice bigger. So you can do the same trick with this one, and you can continue, and it will grow. If you are not sure that it will be aperiodic, what you can do, you can actually sometimes embed the same thing in a bigger thing in a different way. And you can alternate between these 2 ways, say 1, 2, 2, 2, 1, 2, 2, 2, and easily you get something aperiodic. So it's an easy exercise to prove. Now, the question which people were asking, whether there is such tiles that there is no periodic tiling, but only a periodic one. But actually, it's interesting that people first ask a different question. And the question people asked it, if I give you 2 tiles or 5 tiles, for example, these 2 rhombi, is there a computer program which will tell me whether I can tile everything? Again, I think that there is an infinite number of both. So let's just do a few exercises to see that it's not real. So let's take these 2 tiles. So they look like real puzzle pieces from real puzzle. You have infinite number of boths. So can you tile the plane? Yes, yeah, who? Well, okay, you already have a chocolate. I guess there was someone. So any suggestions how to tile? Yes, yeah, Fiona. Okay, up, yeah. So you move one into the other, so they click. And then it's kind of, you see that you can move to from the bottom in a different order. So it's blue, red, red, blue. And then, well, you just continue like that. So it's not a big thing. But you see it immediately. Now what about these tiles? So who knows the answer? Oops. Yeah. Yeah, who knows the answer? Well, let's maybe, okay, I'll give a hint. So we do this. What would be the next thing? Yeah, blue on the right, okay. Now, can you move the third one? So here it's quite easy because there is only one way to add each next one, and then you see that it's not. So in these 2 cases, a simple computer program would work because there is only one in any given place, only one tile will fit, and then you arrive at contradiction very fast. And the second thing, you arrive at fundamental domain. Now, this question, whether there is a program, was asked by Hao Wang, a Chinese-American mathematician and philosopher and logician. And he asked, is there an algorithm to decide whether there exists a tiling? So you can ask, for example, suppose we have, like in this case, 11 tiles, not just 2. Of course, they're different shape, then it becomes complicated. So he suggests to color-code them. So it's like dominoes. You're only allowed to put 2 tiles together if they have the same color of the boundary. It's not exactly as these protrusions, but one can show easily that you can reduce. So for example, these 11 pieces, they correspond to those. You can put only so that yellow touches yellow, red touches red. So here there are 4 colors and 11 pieces. So those are called Wang tiles. So he asked this question, and the answer was given by his student Berger, who said that this problem is undecidable. So this is an example of the previous example with 11 tiles also works. This is an example of 18 tiles I stole from the Wikipedia. An example that you start tiling and you see very fast that you don't seem to have something periodic. So actually Berger proved something much more interesting. He proved that you can embed Turing machine into this. So there is a set of tiles, in particular this one, so that for any program, there is a first row which will execute this program. So since it has a Turing machine, it basically as complicated as the universe. It has everything inside, including, aperiodic tiles. And it was false. It was sort of Wang's observation that if there is no program, then the thing which is tiled but no program, it means that it's a periodic tiling, because otherwise you would just look for this period. So it's very interesting, because from this there is also a relation to cellular automata and many other nice things. And since then, people they progressively decreased the number of tiles. For Wang tiles, the lowest number is 11, but for arbitrary tiles, it was decreased. So Knut played the role, Don Knuth of the Art of Programming and Tech fame. And Roger Penrose, who got the Nobel Prize for the black holes, he reduced to 2 tiles, which are 2 rhombi. I have shown they are rhombus with angles 180 degrees divided by 5 and twice 180 degrees divided by 5. So, of course, if I take rhombi, there is a periodic tiling. You just take the square tiling, but you can make protrusions, and you have these things which have, if you see, they repeat, but they're not exactly the same. So I don't know who has heard of Penrose tilings before. Probably they are very, very popular in Martin Gardner's books. Well, everyone who has heard can take chocolate after the end of the talk. So this is Sir Roger at the Texas A&M Math Department, where the floor is covered with. Actually, for a while, you could buy these tiles. Now you can buy the Einstein tiles. So this is was all that people thought that you need 2. People tried to prove or disprove. Someone came up with a non-connected tile. And then what is really remarkable, that the person who came up with this Einstein tile, David Smith, so he's actually not a scientist. He just likes mathematics. And he was playing, and he got this idea, and it looked like that. He wrote a letter to director of New York Museum of Mathematics, and then together with 2 colleagues, they actually made a proof. And the first tile like this, it's actually, I was really nice. You can play it. It's actually nicer to play with it because it's just a equilateral triangle with 2/3, 2/3, and 1/3 attached on different sides. So it took me about, I was having dinner, my kids were away, so I spent the dinner trying to prove, and I found another proof that it's a periodic tiling, and it's actually, it has some relation to 6-vertex model I will be speaking later. So you immediately, the first thing you can try to show that you cannot tile within the plane without flipping it over. So, and every tiling has 3/4 one side and 1/4 the other side. So there is this sort of chirality in tilings. So they published a paper with 3 mathematicians, and Meyerson, Kaplan, and Goodman Strauss. And then they found another thing which you don't have to flip over. This is the one I have here. You're welcome to play with it. Now, of course, if you ask a question, how does one prove that you can tile the whole thing with this thing? You can try to do it experimentally, just tile this board. It's actually a lot of fun, because sometimes you run in a sort of cul-de-sac, in a dead end, and then usually 1 step back is enough to continue. So there are this self-similar transformation, very much like for the gamma shape. And then what you do, you just alternate them, and you see you get from small thing to bigger thing, and so on and so on. So sometimes you use it for 2 figures. They call this shape a monk, and the first one is a ghost, and this is a monk. You should imagine like a Buddhist monk contemplating something on the top of the Himalayas. And then, it's slightly more difficult to show that it's a periodic, but it's really amazing that people have not found it like in 50 years. I remember when I was a school kid, I read Martin Gardner books of Scientific American, and these Penrose tiles were very popular. So and I think it's an open question whether it's the easiest tile you can come up with. So it has, I think, 11 sides. So all the sides are the same length, only this one is twice longer, and there are nice angles. So the other one is slightly easier, so it's a nice thing. Okay, so that was sort of interlude, which you can ask the question, well, okay, we are doing high energy physics, why do we care about whether one can tile a plane? Actually, I want to point out that people received Nobel Prize for quasi-crystals. So in principle, if you can coat a molecule which has this thing, this shape, and you do like graphene type two-dimensional structure, you will get a periodic crystal, and then it will have some interesting electromagnetic properties as a result. So it's not a totally empty question, and it's not, statistical physics is very close to high energy physics. Actually, in some sense, it's today more interesting because experimentally you still can do new experiments at a fraction of the cost of Large Hadron Collider. So it's kind of high energy physics, but on a shoestring budget. Well, compared to LHC, of course. But we ask a question which is more related to statistical physics or physics in general, but also to combinatorics and many other areas. How many tilings are there? So suppose you can tile. So let's start with this. It's like a canonical tile. It's like one of the tiles I had on a picture, only it is symmetric. So there are two possible positions, if you assume that it's parallel to the axis. So there are two possible positions, and then you ask a question. So can you tile the plane? So who knows the answer? I still have chocolates. I'm not going to take them back. So can you tile the plane with it? Okay. Why? Oh, actually, I first thrown it and then, well, I know how to throw. You have to know how to catch. Yeah, that's actually more difficult. Okay, he got your chocolate. You got it. Okay. So how do you tile? Like, okay, so it's where should I put the next one? So I put it on the side, and there is only one way to put it. Now, maybe I'll just do it myself because I have a mic and you don't. So you can just do it periodically like a chessboard fashion. So that's easier. So that's easy. It's like the first picture, but it's more symmetric. But let's ask a question. How many tilings of an M by M rectangle? And I have to add this remark because I gave this talk once, and of course there was some boring mathematician who said that you can tile a rectangle because there are these protrusions. But if up to these protrusions, mathematicians can be really annoying. Yeah. So suppose you want to tile n by n rectangle. Let's say 2 by 2. How many ways to tile it? 2. Okay. Well, okay. Jan, you get a big one because you already have a small one. No, you don't get it. Yeah. So what is the second way? Well, the second way it's actually quite easy because basically you start at the corner, and there are two ways to start. You can put it either horizontally or vertically. But once you put one, you are more or less forced to do everything. It's kind of like physics analog would be a sort of crystallic structure that if one molecule is in some position, it immediately freezes everything else in one position. So that would be physics analog. It's quite physical. There are such things. So there are two, basically, it depends on boundary conditions, but boundary conditions is just one vertex. So there are only two ways. Okay. Now let's try to do the next one. So there are only two, this one and this one rotated. So let's take the red one here on this picture. So suppose you do the red one. Okay, can you tile the plane? So who knows the answer? Okay, can you? How? What's the? Yeah, you just stack the row after row, and it's sort of the same thing like before. You can do, for fun of it, different things. For example, the other row you can do in different direction if you are into doing something quirky. But, or you can do like chessboard coloring. Now the question is, how many ways to tile an M by M rectangle, or 2 by 2 to start with? So that's if you tell me the answer, I'll give you a big one. 1? No. Yeah, no chocolate for you, no. Not, yes. Sorry? No, for the full plane it's infinite. That kind of hinted at it, but because you can intermittently do different rows, like black. You can do red, then black, then red. So it's but for like a big square, like 10 by 10, how many? Okay, let's try to do it together. So it's so how many ways are there to put the thing in the corner? So how many ways to put the thing in the corner? 4, because there are 4 rotations. They're actually represented here. So let's put these 4 aside mentally. Actually, it's good to remember that 4 is 2 times 2. It will be nicer. You can think that it's 2 here and 2 here. Okay, how many ways to put the 1 here? 2. Yes, let's put it like that, 2. 1. And the next one, how many ways? 2. So there is 2 times 2 times 2. Now let's proceed this side. How many ways to put this here? 2 again. And this here also 2. So if you have 3 by 3, you have 2, 2, 2, 2, 2, 2. So n times 2, m times 2. So n plus m to the... Now let's do the interior. How many ways to put it here? Only 1. And then there is this sort of miracle that, well, let me just put them in black because they don't mean anything. They don't add any degrees of freedom. That inside, always there is only a single way to put it. So basically, here, everything was decided by the 1 corner, here by 2 sides. So it's, and here the corner had 2 choices, and here this side has 2, and this side has 2. So this is, again, is sort of a physical situation that you can do anything on boundary, then it freezes inside. One can easily come up with some compounds where the quasicrystals will have it. But what we usually see, it means that it's sort of a frozen absolute zero situation. But usually what we expect in physics, that the number of ways is exponent of the area. So it's that in each element of area you have some freedom, and then if you have area like 100 square meters, that it's like a to the power 100, unless you are at 0 temperature. So let's do, well, yeah, before we do that, let's do, you see, I choose all the possible shapes where there are 2 triangles popping out and 2 triangles coming in. Now, suppose you have, I have now all the possible puzzle pieces. Suppose you have 3 triangles coming out and 1 coming in. Can you tile with this? Sorry? You mean here? Yeah. Well, I don't mix the other one. Suppose I only use the yellow one. Can I tile the plane? No. Why? Yes, yes. You know, you can imagine that these 2, and we'll see this later, that they're like a system of pipes, where the water goes here north and west and comes in from east and south. So if you assemble things for that, it's like a perfect plumbing system. Very rarely, even in Switzerland, you see perfect plumbing system without water going out of something. But here, it means that there is more water coming out of this. And once you have big enough square, so 2 by 2 you can do. But then, you see, it's already much harder, so at one point you won't be able to do. You can do 1 more row, but 4 by 4 already you can do, because there is overproduction of water. So this is just the answer why I didn't use the other ones. Yes? 1 more for the kids. We'll come to this later, so I count these things as 6 different ones. So if I count rotations as a different one. So these 2 are different. These 2 are different. Yeah, they are different. They are obviously different. Oh, well, okay. So here, if you factor this out, you get 1. Here, if you factor this out, you get 2 to the power n plus m divided by 2 or something. So it's like, you know, my original education is a complex analyst, or like a harmonic analyst. We do everything up to a constant. So it's like Littlewood's joke was that all the formulas I write in my calculus class up to a constant 2, or constant pi, or constant I, or the product thereof. So it's... OK, suppose I use 2 of them. How many tilings are there of n by m rectangle? Who has some suggestions from above and from below? Because it's not easy. It's not easy. Okay, from above or from below. Let's do above is easy. It's very easy to write some estimate from above. So suppose we did some, so I will make a hint, suppose we did some boundary. Actually, when you do boundary, you kind of see that there are two ways always to put a red one and one way to put blue one. So there are three ways to continue the boundary. Always there are three ways to continue the boundary. Like, for example, here and here. Well, here I could have, here I can put red like that, or blue, blue horizontally. So there are three ways. So the boundary influence is easy. It's 3 times 3 times 3, 3 times 3 times 3, and 6 in this corner. But suppose I start doing inside. So how many ways to fill this one? 1, because blue doesn't work. Okay. How many ways to fill this one? Well, also 1, so we're out of luck. How many ways to fill this one? 2, good, because look, you can fill this, or you can put a blue one. So an exercise that always there is either one way to fill or 2 ways to fill. So there is always only one way to put red one, and sometimes you can put blue one. So basically, what estimate from above this gives up to a constant? I don't worry about constants, so even constants to the power n. I'm an analyst. Remember, that's the main take away from the talk. So it's what's the estimate from above? Yeah, that it's assume that we disregard the boundary, but suppose we fill the boundary. What's the estimate from above? How many ways to fill area A? 2 to the power A. That's an easy estimate. Okay, so it from above it grows like some number, 2 to the power area. So I should throw some chocolate there. But yeah, okay. So it's. You know, I broke a couple of years ago my hand skiing, so it's made out of titanium, so I have to, doctor tell me that I have to exercise throwing chocolates. Okay, so far it works. Now from below. So from below, we want to come up with some way to have this sort of exponential, that there is some freedom per area of the area. So any suggestions how to do that? Okay, I will give you a hint. That's the number. That's the answer which we will prove in a second. So it's root of order 4 of 2 to the power nm. How can you get 2 to the power 1/4? Well, it's the same as if you have a number 2 for every how many squares? If you have root of order 4 of number 2 per square, then how many squares you need to get factor 2? 4. Okay. So there should be some freedom for 4 squares. Okay, let's try to tile 4 squares with blue and red. So I will do it, let me see, like this, and then like that, and then another red one, like this. Okay. So this is a hint what one should do. So any suggestions how to do similar block, but differently? It's very, yeah, yes. Okay. Oh, wait a second. No, I did it wrong. I think I did something wrong. Yeah, it's wait a second. Yeah, that's, yeah. Okay. Like that, yeah? Okay, and where the red one goes? Okay, the bottom. Okay, no, oh, no, it's difficult. You know, it's undecidable by computer or Professor Smirnov, so it's... Okay, yeah, let's you get one more. No, okay, your neighbor got it, okay. Yeah, at least I didn't kill anyone with my titanium hand. So you see, these 2 blocks, they look exactly the same from outside, but they're different. And it's clear you can tile with them the whole plane. Because they just look like a blue block horizontal and blue block, so you can just alternate vertical and horizontal. So it's like in the blue one, so you alternate these blocks horizontally or vertically. But there are 2 of them. For each of them, there are 2 choices, so you get 2 to the power area over 4. So we see that this model is already something non-trivial, with some non-trivial answer. It's a number between root of order of 4 of 2 and 2. We didn't prove that it's a to the area. Of course, it's obvious for a physicist that it should be then area a to the power area, but proof it's actually here one can prove it. But then the question is, what is this number? So I ask another question: what is a random tiling? Wait a second. I thought. So suppose we counted the tilings, then we can define partition function z to be a number of tilings, which is basically sum of number 1 for every tiling we have. And we can choose uniformly 1 at random, meaning that probability of each tiling is 1 over z. So what will we see? If you do it with this, you will see just red and blue dots, which won't explain you much. I will tell you later how to see something. But a nice example, if you take rhombi, the usual rhombi, which is 2 equilateral triangles, 60 degrees, 120, 60, 120, and tile a hexagon. If you tile a hexagon, and there is a computer program which really chooses 1 at random, and you cover them in 3 colors, well, depending on the rotation. So it's like you see a picture of boxes in a corner of a room. So this is actually a random picture, and the question, what will you see? So this has been studied, like as we speak, there is a conference in LA about that. So this is a big hexagon, and it's a tiling which is perfectly selected at random by a trick invented by Jim Propp, which is called sampling from the past. It's a trick how to work with Markov chains that used in computer science very widely. And you observe an interesting thing. It looks random inside, but then there is a frozen 6 areas. They're easy to explain because if you put in the corner of warehouse, so it's like Amazon delivery or something, boxes, then most likely here there won't be boxes in most cases, because if you put here, you have to put a lot below them, and on the other hand, this corner will be filled. And it's a theorem that there are frozen zones, so people understand fairly well. If you take another shape, there might be some interesting shape of frozen zones. There are always algebraic curves. And what are people trying to prove now? That what you see here, it's a random height function. It's a random 3-dimensional function. Everyone sees 3-dimensional picture usually. If you have bifocal vision, most people do, then they see 3-dimensional picture. Then you see a random height function, and this converges to what mathematicians call Gaussian free field, or physicists call a massless boson. And the interesting thing that we don't understand very well. So there is a conjecture, what is the conformal metric for it, due to Kenyon and Okounkov and Kenyon, Okounkov, Sheffield, and we are sort of about to prove it. I mean, all the mathematicians, but it's okay. So that was part 2, and then there is a third part, which is the first interlude. Why do we count tilings? And this has many relations. So it's to statistical physics, to theory and combinatorics, and I will start with statistical physics. And this is a question which was asked by Linus Pauling. So he's dear to me because he also a graduate of Caltech and worked there for a long time until he got the second Nobel Prize and was forced to resign because of the second Nobel Prize. The second one was for peace. And back then it wasn't fashionable to be peaceful. So, and he went to Stanford. So he got one for chemistry and one for disarmament, and he was actually instrumental in people realizing that DNA has a spiral structure. He was the first to observe spiral structure in molecules, and actually he was playing origami, sort of folding paper like molecules were, and then so that like naturally spiral structure should appear. Okay, so he asked a question: what is the residual entropy of water ice? So it's 0 degrees when there is sort of no temperature. So basically you freeze. How many configurations are there? And he asked as a simple model. Let's assume that we have a 2-dimensional water ice. It looks like very far away from reality, because the water doesn't have 90 degrees angle between hydrogen atoms. But the interesting thing that now you can have this. You can have one layer of water on graphene, and it actually looks surprisingly close to this. But this is a simple model. So you assume that oxygen atoms occupy vertices of square lattice, and there cannot be 2 hydrogen atoms in the same place. So basically from every vertex there are 2 arrows. It can be like here left and up, or left and right, but here there is only 1 hydrogen atom, exactly 1. So the air is from above. Here it's from below. So you can, and the number of these tile links is expected to grow like a to the power area. Well, you should be careful about boundary conditions. You can do it on a torus, so you can impose like here. And the question was, what is A? So logarithm of A is the residual entropy. And this is exactly the game we were playing. It's just exactly these 6 puzzle pieces. So this is called 6-vertex model because of that. And it was a famous result, Elliott-Leap in 1967, that A is 8/3 square roots of 3. So I will say a couple of more words later, but this was a big sort of period of integrability or exact solvability of lattice model, which was started with paper of Ansager, who was also a chemist, also Nobel Prize in chemistry, or maybe Kramerson 1 year sometime before, and it still hasn't finished. We have heard it mentioned a couple of times during this conference, that there is some sort of mysterious thing, well, maybe not mysterious, but has several different explanations why on a plane we can calculate things exactly, whereas in 3D normally we cannot. If I pose the same question in 3D, we cannot. So this is this famous result. So Elliott-Leap, actually, he got Gauss Prize at the last ICM 2 years ago for his life achievements, and this was one of the achievements which was mentioned. This is just this puzzle game. You count how many things you have. It's interesting that, well, Hugo Gemini, Ioana Manolescu, and their colleagues, they are now trying to prove that this model is conformally invariant as MI by several different methods, and they proved it's rotationally invariant, but on the way they got a simpler proof of this Elliott-Leap thing. It's called usually a 6-vertex model, and why? Because what you can do, you can just draw arrows on a square lattice. So every puzzle piece corresponds to some vertex of a lattice, and you draw the arrows going out in the direction where there are these protrusions. And if you have only these 6 puzzle pieces, you don't use these broken ones, you have a perfect plumbing system that water just moves around without, there are no vertices which are sources or sinks. So it's like a divergence-free vector field. So these people, why people call it a 6-vertex model. There are 2 remarks I want to make. So I said that we were counting that 1 is the weight of every configuration, and then we count number of tilings, so the partition function is sum of 1s. But we can assign weights to these 6 puzzle pieces, like 6 numbers, A1, A2, B1, B2, C1, C2, and count that the weight of a thing is a product of weights over tile. So for example, suppose you have weights 1, 1, 1, 1, 5, 5. Then the weight of this configuration would be 1, 1, 5, 5, 5 times 5 times 1 times 1, 25. This one would have weight, oh, the same 25, yeah. Okay, so this is, and then there is a usual trick. If you have weight on some configuration, some measure, you can make probability out of it, but normalizing the measure to have total sum of 1 by dividing by z. Okay, so this is called 6-vertex model in general with general weights. It's already interesting enough that what we'll mention later today, if you have weights 1, 1, 1, 1, cc. So this is already very interesting and has many physical problems of interest inside. The other object which is already present on this thing is called height function. So you see, suppose you have a geographic map. In geographic map, how does it look like? You draw some loops, and if you have 3 concentric loops, to need to know whether it's Monte Bianco or Mariana Trench, you need to know orientation, whether they're oriented clockwise or counterclockwise, whether it's a hill or a hole. So basically, what you do, you just draw like arrows around these things, and if arrows go counterclockwise, you have hill, clockwise, you have a hole. So here it's the same thing. You have a system of arrows, and then it's basically what you can do. You can define height function up to a constant, so you start dividing at 0 here, and whenever you cross a line, you increase it by by 1 if your line goes to the right. If it goes to the left, you decrease by 1. And then it's consistent around the vertex because you cross 2 which are going out and 2 which are coming in. So it's an easy exercise in mathematics that there is a unique height function. So the analog of this would be that if you have a divergence-free vector field, then it's a curl of some other vector field. So this something, or if you have a curl-free vector field, it's a gradient of some function. So it's the same thing. Okay, so this is just basically two things that the height function is, so one possible way you can, instead of tiles, you can consider a height function so that the difference between each two nearby tiles is exactly 1, and that would be the same object. So it's this. If I erase the arrows and I have these numbers here, I still can reconstruct the arrows uniquely. So this is how physicists play with it. And here I have stolen a picture from Filippo Di Francesco's paper. It just shows that there are many, many bijections. So we already explored that you have bijection between these and height functions, but there are really many combinatorial objects. For example, you can pull it all the way through to this sort of hexagonal tilings. So it's really in the middle of statistical physics or integrable combinatorics. And what is statistical physics? Okay, that's the popular part of the talk. It's when you have a complicated system, you can study all the parts. If I have like a glass of water, there are like zillions of zillions of zillions, literally speaking, molecules of water there. I can write the motion equations. There will be 6 times zillions of zillions of zillions equations. Can I solve them? Well, probably not. What people do, people starting with Boltzmann and Gibbs, they do just statistics of it, how many molecules with which speed. So statistical physics is when you have a system which has many, many simple parts, which do undergo some simple rules, and the sum of them is complicated. So here there are, for example, this is an DNA unfolding, so that's an actual image from Livermore Lab. This is erosion at computer simulation. This is acid on the surface of aluminum. This is computer simulation of a forest fire. And then, for example, these are crystals of gold. And I realized that when I was in school in Soviet Union, we had this very nice journal which was called Quantum. It's a bit like American Mathematical Monthly, but it's more physics and math for school children. And it had a series of books. So if you know the Greek letters, you can read that it's physics and geometry, physica and geometria of disorder. Well, disorder would be harder to guess if you don't know Slavic languages. So it was 82, and you see again forest fire, and these are actually pictures from that book. It's a big and noble area of physics. It has very close relation to high energy physics. Why? Because if you want to define a field theory, one of the ways to define field theory, and the easiest to do it rigorously, is to define something discrete on a lattice and then try to pass to a limit. So this is kind of relation to field theories. And this is somehow how this combinatorial thing fits in the bigger picture. Okay, yeah, this is, let's go how much time I have. So that's the second part about tilings and loops. So what does random tiling look like? How to see structure in randomness? Interestingly enough, as I said, I'm complex analyst, and I like to it in the plane because complex numbers appear in the plane. So let's do very easy loop model. We just have 2 tiles. Actually, it's the same tile with 2 rotations. It's very easy to count how many tilings are there. It's just 2 to the power area, because you can put one way or another way. And they always fit because I use lines everywhere. I did cover the lines. What is difficult to see whether there are connections, because you see I changed one tile and the red dots are no longer connected. So there are, even here you have difficult things. But what you can do, you can weight this picture by n to the power number of loops. So for example, in this picture there are 2 loops. So weight is n squared. In this picture, there are 3 loops, so the weight is n cubed. So the difficulty compared to the product of weights of tiles is that it's a non-local weight. So it's much more difficult, but then it's much more interesting. And then you play the same probability that you take like partition function, this sum, and then you normalize by it to get the probability measures. So the question is called FK loop model because Fortuyn and Castellane, they realized that random cluster model, so it's a model, so you do random clusters on a blue lattice, then you can draw on a dual lattice, yellow lattice, dual clusters. And then if you draw the loops in between them, then model with complicated cluster weights, it becomes this loop model. But it's not important if you've never seen it. It's just a remark for those who have heard the words random cluster model. The question is, so how to study it? Well, the first thing is, of course, it's easier to do it without boundary condition on torus, cylinder, or plane. Or you can just remove the tiles which are on the boundary, just leave these half loops, and just study this white region. So we, for example, here there is 2 by 2 region, there are 4 squares, there are 2 to the power 4 possible relations, and you can study what happens with them, and then do it for bigger things. So how do we get weights local? And there is a very nice trick, so it's, again, every math talk should have something a first-year student should understand. So there is a very nice trick which is due to Baxter, of young Baxter fame and many other things. So we have this weight n per loop. So we solve the quadratic equation, mu plus mu inverse equal to n. So it's basically mu squared plus 1 is equal to n times mu. So there is some generally complex solution mu. And we weight counterclockwise loops by mu. So in this case, there are 3 loops which are counterclockwise. We oriented them, and the weight is mu cube. Now, in this case, we weight the other direction of loop mu inverse. So this is mu, this is mu, this is mu inverse, so it's mu squared times mu inverse, so it's mu. So far, it's not any easier, because we have oriented loops, not loops, and we have complex weights. But then there is a trick which makes it easier. So let's take number nu, so that nu to the power 4 is equal to mu. You know, remember, we're now in a complex plane, so every number has root of every degree. And then we weight left turns by nu, right turns by nu inverse. So we now weight individual turns. So for example, what happens with this loop? What will be the weight of this loop, of this cycle? Sorry? No, there are left turns. So this left turn, left turn, left turn, left turn. So the weight of this loop is what? Nu to the power 4. So that's mu. And this one? Yeah, it's the same. It's nu to the power 4. Yeah, so it's you should also have have a few. So it's because you see, basically every cycle has total turn of 360 degrees. You might wiggle left and right, but when you wiggle left and right, they cancel out. So every cycle in one direction has weight mu, in another direction has weight mu inverse. So basically, the weights became local, because now these mu weights, they're just product of weights of these plackets. And if you forget the orientation, the weights are local. If you forget the orientation, then you get the original weights, because you have mu plus mu inverse and non-oriented things. But also you got the height function, because now there are arrows, so you have the height functions. For example, for this one, it's, you see there are 2 hills. So okay, so this is like Alps, this is Dolomites, and this is whatever, Mediterranean Sea. So there are 2 positive things. Of course, you can never have only positive things. You should have negative things. Now, the negative things are that the weights are complex, and the normalized measure is no longer probabilistic. So the total mass of the measure might be very big if you add absolute values. So this is the problem, but it makes the life interesting. So it's harder to do probability, because you have to work with complex measures, but it makes the life interesting. Now, instead of 2 puzzle pieces, we now have 8. You see that you can orient in different directions. So there are 2 orientations, and then there are 2 arrows, so there are 4 directions. What is the weight of this guy? What is the weight of the guy? There is 1 left turn, 1 right turn, so what is the weight? Sorry? 1. Yeah, okay, you get it. So it's, the weight is 1. Nu times nu inverse here is the same, nu times nu inverse, left and right, they cancel out, left and right. And these are 2 left turns, so it's nu squared, 2 right turns, nu in minus 2. And here it's the other way around. But what we can do, we can forget about how the arrows are connected. So we can join these 2 in this thing. So if it's water flowing, we don't really care. We can think that it's mixing up there. And then if you join them, you get nu squared plus nu to the power minus 2. But if we assume that nu bar is equal to nu inverse, so if nu is a unitary number on unit circle, then what we get that this is a real number, because it will be just nu squared plus nu bar squared. So this is a bit of complex analysis. So basically, if nu has this property, and you have this property for n between minus 2 and 2, then you will have real weights. So you get this puzzle piece model with real weights, 1, 1, 1, 1, CC. And we started with a model which was totally difficult with global things. Now it's local. Of course, there is some catch. And the catch is that people don't know how to work with the boundary. Boundary conditions for this model and for the other model are different, and somehow they are not quite, okay, people didn't know, let's say that. Okay, so this, then there is also height function, and the weights only depend on the gradient of the height function. So in these 4 cases, it's flat, so the weight is 1, and there are 2 shadow cases, so it's not 1. And then it's already coming much closer to the topic of this subject. So this allowed to physicists Denise and Nienhuis, to Dutch physicists, to come up with conformal field theory a few years before conformal field. So they came up with conformal theory without explicitly saying these words. So they came up with something which was called Coulomb-Gas approach. And the reasoning was like that. So you have this height function, a random height function. There is a weight for every configuration. And then we pass to scaling limit. So we sort of shrink the lattice, send the mesh to 0. We rescale appropriately the height of the height function. So we should have a random function in continuum. And then the weight depends only on the gradient. So we write the simplest weight which can depend on the gradient. And it should be rotationally invariant. So it should start with gradient squared. Maybe there are other terms. But they postulate that there is only this term. And there is constant in front, which depends on n, blah, blah, blah. What happens is that maybe an important thing is that if you do it 1D, if you start with height function that goes plus minus 1 and 1D, it's just trajectory of random walk. Then the limit is the Brownian motion, which is a random function, which is called Wiener process. You can write it as a random Fourier series, as Norbert Wiener did. So now here we have a random function on a domain, and we pass to a limit. Unfortunately, we don't get a random function. We get a random distribution in the sense of Warren-Schwarz. This is a random distribution which is called massless boson or Gaussian free field if you're a mathematician. But it's rather tame, so people can study it and then can deduce all the things. Now, what's the problem with this beautiful approach? It came 2 years before conformal field theory. The problem is that there are several unverified steps. So there are a few leaps of faith. And if you as a mathematician try to read their paper, you say, okay, I can split this step in 2 lemmas, this step in 3 lemmas, this step I can't make any sense at all. And then you can't prove this 5 lemmas, and the third step you can't make any sense at all, so we don't know what to do. And one problem is that they only could do it on a torus, on a cylinder, because they couldn't do boundary conditions. And I spent a few weeks with John Carter, a few weeks with Nienhuis trying to figure it out, and at the time we failed. Okay, so this was the second part. Now there are 2 parts remaining, so I go to Alexei Ray. There will be singularity at the end of the talk. I will talk faster and faster and faster and faster. So what's so special about 2D? So the special about 2D is, well, there were, I would say, 3 things. So first, starting with the algorithm, there were exact solutions in 2D. It's still mysterious to me. I wrote some of the exact solutions, why they work. Because a few things, they kind of click together, and I think, like, well, several people in the audience know it as well as I do, or even better, that there is really like miracles. Well, Young-Baxter equations, for one thing. Then in '84, conformal field theory happened, and Nienhuis was kind of 2 years before, and indirectly there is conformal there. And then mathematically we tried to make sense of conformal field theory, and we came up with other methods which in the end were completely orthogonal, so now physicists also use them. So it's Schramm-Leuwenhoek evolution, discrete complex geometry. But there are like fabulous predictions in statistical physics. The one which was predicted by Denise and which we proved is that Hausdorff dimension of percolation cluster is 91/48. When I was in school or in university, I never thought I would be proving theorems with 91/48 being an exact dimension. Or the one which, if you want to become rich and famous, you can prove this prediction that the number of lengths and simple, okay, you're not really rich and not very famous, just among mathematicians and physicists. This prediction of Nienhuis, which is still unproved, that if you count length and simple curve on a lattice, then they grow like mu to the power n. That's easy to prove. Mu depends on the lattice, also easy to prove. For hexagonal lattice, Hugo Dominio and myself will prove that it's actually square root of 2 plus square root of 2. But then there is a next term which is more precise, and it has 11/32. So there are this very thing that there was a long road through this. So there was like renormalization group theory and conformal field theory and the famous paper of Belavin, Polyakov, Zamaochik, where they didn't treat with boundary. Kardzhi treated boundary, and actually Zamaochik and Kardzhi just got a month ago in LA the breakthrough prize for this, mostly for this older work of that. Polyakov had it longer before. And I think I will show just 2 slides. So what is conformal field theory? It's a field theory which is conformally invariant. But lattice is not conformally invariant. If I study like tiling of square lattice, conformal maps, like Mercator projection is a conformal map which preserves angles but change distance, doesn't send to lattice. So it's not the same model. But what people postulated, if you look for very far away, so the length of the lattice mesh sends to 0, you see the same picture. So it's difficult because it's not a discrete statement. It should go very, very far away. And the way we managed to prove such things was sort of, well, one example is that random walk is not conformally invariant, but Brownian motion is. And the way we managed to prove some of these conjectures by observing some sort of discrete analytic structure on a lattice. Like, say, you have square lattice, like the lattice here. You define function on edges. And then for every square, for example, you have Cauchy-Riemann relations, or Kirchhoff laws, if you wish. And then it's the local information, which often is easy to check. But then it kind of comes to a global thing. It's like if you know the vector field is divergence-free, then you have these Gauss and Stokes theorems that the flux through the boundary is 0. So you can pass to global things. And there are many, like there are many discretization of complex analysis. There is no canonical ones. For example, there is one with circle packings, it's non-linear one, and there is one with squares, and there is this beautiful picture which makes me dizzy. Oh, really it does. So this is, well, there are several models which we're able to do due to some beautiful things which happen there. But for example, self-avoiding walk, these simple curves on the lattice, so polymers like DNA unfolding, we cannot do yet. Okay. And this is the last part, and I believe that, actually I believe I have 8 minutes. Am I correct? I started at, now is it less? You think less? Yeah, okay, because no, I didn't start at 5:30, 5:30. We were still sort of, okay, but do I have 8 minutes, or who is the boss? Yeah, that's, okay. I have chocolate if someone is unhappy, yeah. Okay, so I will try to speak about some old recent work. So I've spent significant amount of time trying to figure out how to do this Dutch approach, Coulomb-Gas approach with the domain with the boundary. And I think I figured it out. So we spent also a lot of time with Bernard Nienhuis and with Card thinking about it. But then, well, with time maybe we become wiser. So what we do, let's start with the domain and start with this picture of this oriented complex thing. Again, we weighted by these complex numbers. So complex is nice because I'm complex analyst by education. So I'm a complex person, but not in the, okay, I'm simple person, but well, okay, whatever. So it's, we want study height function. Well, first we need to mind boundary conditions. So what I suggest, we just erase all these half things. And then in this particular picture, we have one source on the boundary, one sink on the boundary. So there is a water which flows inside. Somehow it reaches from here to here. So it's clear that there is a path between source and sink because this cannot disappear if it's a finite domain. But we want to find a discrete analytic function. We want to have an analytic function of z. So we have to distinguish this point z in some way. So of course we can ask, what is the probability that this curve passes through z? I tried, doesn't quite work. So what we do, we reverse the flow of half of this arc. So we reverse it, so we now have two sources on the boundary and one sink inside. So this sink which sucks 2 gallons per minute, and each source is a half source, so it's 1 gallon per minute. Now, is there something wrong? Who sees something wrong with the height function? What's wrong with the height function? Yeah, at this point, exactly. At this point, it's like science fiction. There is this pole at this point. So if I walk around, so say it's the top of Mont Blanc, so I walk around it, and I cross the red line, I cross blue line, and suddenly I'm 2 meters higher. So it's kind of monodromy. So it's like in science fiction, you have these loops through which you pass into other dimensions. So it's just arrive to the same point, but 2 meters higher. If you walk 10 times, you are 20 meters higher. But it's like a surface of a logarithm. It's a Riemann surface of a logarithm, what we teach, that you just, and very easy behavior. It's a function. You can study a function on a Riemann surface, especially if it has simple behavior that on each sheet it's plus 2 meters. It's a very easy behavior. So we just, okay. Now, this actually can be resolved. You can add, because here there are 2 gallons in per minute, you can just put another green pipe which sucks it out, which is kind of imaginary pipe. It's just there for consistency. But then you can put it in different ways. Oh, I thought I had a picture of a different way. If you move this pipe to a different location, you have different height function. So basically, it's this usual trick we teach in Complex Analysis 101, that if you have this Riemann surface which is branching, you should take a crosscut. But it's important how to take crosscut, because then representation changes. But otherwise, it's very easy, but it's very, okay, so let's trace both connecting curves. I covered both of them by red. And let's change the weight. So we had weight nu inverse for blue. Let's make here correction of lambda, lambda nu and lambda nu inverse. And then we take this function with this monodromy, and we take its expectation. And there is a parameter lambda. And then it turns out that what we can do, we can rearrange things at this square. And when we arrange things at this square, so for example, what I can do, I can move this, you see. I don't care what happens elsewhere, but I move this around. But this is a trivial move because I flow up or down this river. But I can make non-trivial move. I can attach this loop to this river. Again, I rearrange only inside. And I have full control over the weights, lambda and nu. And it turns out, so I don't want to bore you, but so there are 4 different pictures when you do rearrangement. So you can calculate all the weights, and then you can ask, just these pictures alone, not all, just this. Do this satisfy Cauchy-Riemann? And this, the satisfying Cauchy-Riemann, it just you plug them into the Cauchy-Riemann equation, you plug these things, you get this huge thing, which is not that bad, it's degree 4 equation, and you can factor it out. And it turns out that there are 2 routes. One route is not interesting, you get it just from flowing up down the river, so it's not interesting. But there is one which is interesting one. And it has some non-trivial relation between lambda and nu. And, well, you can work with it. And this function is then Cauchy-Riemann equation. It's discrete analytic to some extent, not fully. And then there is a simple exercise that if I arrive at this point, then the number of the red turns is exactly 4 times height function at this point. So look these 2 pictures. So the picture on the right, I twisted the picture by 360 degrees. And then the curve from the right made 1 full turn. Curve from the left made from 1 full turn. So when I go from the boundary, h is 0, h is 1, h is 2. So the difference of height, I presume that the crosscut goes up, is equal to 2. But here there are 0 turns, here there are 8 turns. So basically, I can write lambda to the power number of turns as lambda to the power 4 times height function. And it will be the same. This has been done to some extent in physics literature, but not exactly like that. So this would be called electromagnetic operators. But basically, the theorem says that you can write, you can forget these red curves. You just fix the crosscut. And then for appropriate choice of rho, if you weight by rho to the power height function at z, you get a discrete analytic function. And the only difficult thing is that h is defined up to monodromy. So when I sort of twist this point around, the height changes. But the good thing is that you can also do it not for a source, or not for a single, but for a source. And then it's rho to the power minus h because you change the direction of errors. So basically, you can have any combination of plus and minus operators inside, as long as the total charge is 0. F is defined up to monodromies, and every term which has minus charge comes height with plus, plus charge with minus. And that you can write as exponent of sigma pi times the difference things, and it's Cauchy-Riemann in all variables. Now, the interesting thing is that you have this function of 3 points in this case. But they are all defined up to monodromies. So what happens, for example, if I twist 1 point around itself? If I twist it around itself, place where I measure height intersects this green crosscut. So height changes by 2. So the weight changes by rho to the power minus 2. Now what happens if I move 1 point around the other? Well, this point crosses this line, but also plus point crosses that line when you move this. So both of them cross. And you would think that the changes in height cancel out. No, because there are different directions of these 2 things. So h is minus 2, this h is plus 2, but also they come to rho with different signs. So it's actually the same thing, rho to the power 4. And if you combine these 2, basically you would sort of, what is clear for complex analysts or theoretical physicists, is that this function of u and v should behave in u like du to the power sigma. It's not a function, it's a form. dw to the power sigma, but it should be divided by u minus w to the power 2 sigma. So it's kind of a Green's function. If the power sigma is 1/2, that's what you get for Ising modulo and a fermion, it's divided by u minus w. So it's just Green's function for d-bar operator, standard object complex analysis. But generally, you would have a function which has some branching, but it's still sort of a Green's function. And then you can study it, and then you have 1.5 minutes for the last 10 slides. So okay, why coulomb gas I don't explain. Let me maybe just explain that what happens when you fuse two things. So suppose I fuse U and W. So I took them next to each other, but you can really fuse them to one place. So basically, this picture is almost legal. Only the green edge is illegal. It goes in the opposite direction. So you retrieve probability of the green edge. But what is the weight of this picture? You have rho to the power h of u plus minus h of u minus. But if u plus and u minus will be fused, their h's will be the same. So the weight is 1. So basically, you get it without any complex weight. So you actually get access to nabla h from fusing q and w. And what happens if uw is a Riemann boundary value conditions because it has this covariance? What will be the conditions of nabla h? So it's interesting. If you have this covariant object like parafermion, these boundary conditions, when you fuse, it depends what's going on, but usually get either Schwarzen or pre-Schwarzen or pre-Schwarzen. So like in physics, they usually quote Gelfand-Fuchs-Casaikus, but the Schwarz came before Fuchs. Well, at the same time as the other Fuchs of Fuchs in groups came, but before that, so I would call it Schwarz and Casaikus. So this is just a simple sort of calculation. I don't want you to do it. I just show that you start with the formula for f, for example, like this. And then you fuse these 2 points by setting that u is v plus epsilon and sending to 0. And then you can Taylor expand. When you Taylor expand, you get like formulas like that. And then when you open it up, for example, for this particular setting, miraculously, you have term 1, then there is no epsilon term, but term in front of epsilon square is a Schwarzian derivative. Now, if you have not heard Schwarzian derivative before the words, so this is a very beautiful object in complex analysis which measures how far your map is from a Möbius transformation. So it plays very important role there. So this is sort of, I promise that the last 10 minutes will be something new, and last 10 minutes are something new. Well, maybe I'll just give the takeaways. So it's interesting that simple models are often the most interesting because they connect to more things. And thanks relate to many, many, many areas. I just mentioned 2 or 3. The takeaway for physics, it's really, I haven't seen this in CFT literature or even potential theory literature, green function with monodromies. Now we have this massless boson, which you get for field theories with different central charge. So what's the difference? It seems to be the same massless boson. And the difference is in the boundary conditional covariance rule. It's the same one, but when you map it as a different pre-Schwarzen covariance. Well, that naturally arises from fusing fermions. Now, the interesting thing is when you fuse 2 fermions, you expect to get a boson. Why you have 2 spin segments to get a boson? Because you have these conical singularities there. You can say that it's a background charge or something, and this kind of straightens the things up. But it's still a bit mysterious to me. And also, there is still, I think it's certainly, I understand now this on a physical level, but I'm not allowed to publish in physics because I'm in the math department, so I still have to get the full proof.
Thank you, Professor Smirnov. There will now be an opportunity to ask Professor Smirnov a few questions. He'll be joined by Professor Annalisa Massacesi, professor in the Department of Mathematics here at the University of Padua, who will chair this Q&A session. Thank you.
If I answer correctly, I get a chocolate. Thank you, Annalisa.
We can sit comfortably and you can rest a little bit. So even if I may sound repetitive, let me thank you for this beautiful lecture. And let me tell you that we are really grateful that you're here, and yes, it's really honor. So I have a few questions, but I think it's better to start with the audience. So whoever has question, please raise your hands and please.
three-dimensional what?
Volume tilings.
Ah, volume tilings. Look, it's interesting. Let me say like one thing. So the conventional wisdom in mathematics and theoretical physics is that three-dimensional models are not integrable, that you won't have nice exponents like 11 over 32. Now, what I would say that I once made a careful list of all the integrability approaches we use in 2D. Really, it was like several pages. And then I crossed those which absolutely can't work in 3D. And some are remaining. So I think you won't have nice 11 over 42 powers, but you might have, for example, suppose you have a theorem like magnetization exponent of Ising model is equal to the third Betzky number of a torus with two holes. It's a good theorem, it gives you the number, but it's not a rational number, let's say. So there might be something like that we haven't seen so far. There are some theorems that tilings problems are not NP, so they are polynomially hard in 3D. So the problem of finding number of domino tilings of a square, there is an exact formula in 2D. In 3D, it's NP hard. But it doesn't mean that there is no exact solution in the limit. So it's again. So it's an interesting question. We tried to define height function for some dominoes in 3D. We managed to concode some object, but it was too complicated, so we decided not to proceed. I was told by someone that actually some people did something with it, not with algebra, but they invented something similar, but I haven't read the work yet.
For instance, for statistical physics, it seems that's more natural to consider three-dimensional rather than states corresponding to two-dimensional.
Well, I mean, it's debatable. There are many processes which go in 2D, like a forest fire or graphene, or I mean, there are 2D things. Also, of course, 2D CFT is sort of, in some sense, a better baby model for the string theory, so to say. So it's no, of course you are right, but yeah, you are right. But conventional wisdom says that there is no exact solution of Ising model in 3D. And if one gets one, probably he will become rich and famous again. Rich in a limited way, but he will get some salary raise, probably. If he works in US or she works in US, probably he will become famous in our community. Conventional wisdom says it doesn't exist, but I don't see a particular reason why it doesn't exist. So it's very hard to prove that something doesn't exist. So but I don't suggest grad students to work on it. At least not full time, yeah.
Okay, further questions? Yes, I'll bring you okay, you can have one.
So thank you for your very nice talk. Just a curiosity, you've mentioned a couple of times that the Cauchy equations for this discrete complex function was equivalent to Kirchhoff laws. So just this curiosity, could you please explain to could you elaborate on this aspect?
Okay. Let me say two things. Like, first thing is that there is no canonical way to discretize complex analysis, unfortunately. The reason is that in complex analysis, one of the key facts which makes it nice is that product of analytic functions is analytic. Now, when you try to differentiate product of function on a lattice, you use this rule that fg derivative is f prime times g plus f times g prime. It turns out that f prime and g prime then evaluated in different places, just because when you do it as discrete differences, and the whole thing breaks down. All the versions I know of discrete complex analysis, the product of analytic functions is no longer analytic. It might be close to be analytic, but so that's some small problem. And I'm rather opportunistic, so I don't see an ideal thing, so I just use whatever works. What we used for Ising and what turns out has some importance for these pictures like this hexagon was a definition which was specifically adopted to fermions, specifically adopted to square root of dz forms. So it had the equation I've written, where you sum over the square with factors 1, I, minus 1, and minus I. But it has also a dual equation where we sum with factors 1, minus 1, 1, minus 1. And that you don't see as Kirchhoff. But then, let's roll back. So that's the first part. The second part, let's roll back to the usual complex analysis. So usual complex analysis, there is a complex valued function in a complex plane. you can look at complex plane as a real plane, and complex Weyl function is a real vector field. And then if you write Cauchy-Riemann equations like we usually write, ux is equal to vy and vx is equal to minus uy, or I usually confuse the sign, but this just basically means that the x and y axes are like that or like this. So you have two equations. And if you look at them closely, they're very much like saying that the uv vector field is curl-free and divergence-free. To be precise, you need to swap two coordinates. You need to swap u and v. And then, so two Kirchhoff laws for a flow is that it's divergence-free, meaning there are no sources and sinks. And that it's curl-free, that if you put a small turbine, there is no like perpetuum mobile at this place rotating around this turbine. Now, Kirchhoff laws are very nicely formulated in discrete, which was done by Kirchhoff in 1848, and we usually study them in school. So in school they say that if you have like electrical network and you have a node, there is a law of the node, which says that the amount of current which goes out of a vertex sums to 0. So if there are like 2 units coming this direction, 1 unit coming that direction, then there should be 3 units coming from another direction, so 2, 1, minus 3. And then another law is again that there is no kind of curl, no perpetuum mobile, that if you take a face of your planar graph, or on planar graph just some loop, then the flux through this loop again sums to 0. So you have a loop and you go around, say, counterclockwise, then, and if you have like 2 here and 2 here, then here it should be minus 4, so it sums to 0. Otherwise you get perpetuum mobile. So that very nicely can be defined on the discrete lattice, and you observe this for the Minot tiling, so for uniform spanning trees, just exactly like that. For uniform spanning trees, it was, people usually quote that Kirchhoff had it in his book. I tried to find, couldn't find, and someone said that he found it in this book 50 years ago, and people keep quoting this person without actually opening the book. But it was in some other book in 1860s by one of his students or some other paper, so it's rather old. And he basically, people figured out back then that kind of total flux or total current between 2 points, it's related to eigenvalues of Laplacian and such stuff, so they related it to something related to Laplacian, and if you're on the plane, Laplacian relates to conformal geometry. Yeah.
Thank you very much.
Yeah, thank you.
Further questions for the audience in presence?
Oh, I scared everyone. If you ask a question, you get a chocolate. Okay, yeah, I still have a couple of big ones. Yeah, okay, now I'm much worse at throwing when I'm sitting. Oh, no, it's okay. Yeah, that's... But actually, it's a white one. White one doesn't make you happy. You know, it doesn't have serotonin, so it's... let me throw you... No. Okay, sorry.
Okay, so let's say now I want that bag for myself.
Yeah, please.
No. Okay, so a few questions related to being a mathematician / theoretical physicist. Okay. You mentioned in one of your last slides that simple problems are the most interesting. And perhaps long-standing problems, they have often a simple formulation. But what do you think about their solution? I mean, is it still possible nowadays that they have a simple answer, an answer which is easy to explain and communicate?
So thank you. So I think maybe the better version of my statement was that simple models are the best, because simple model usually is related to more things. And an example was the Ising model of ferromagnet, which was, we have a joke in statistical physics that you name models you introduce after your students. So Ising model was introduced by Lenz and named after his student Ising, like student of Castellan Fortuin, there is Fortuin model, and then Potts was student of Cyril Domp, and hence Potts model, etc., etc. So Ising model was very simple, and unfortunately, Ising, he proved there is no phase transition in dimension 1D, and wrongly made a remark in his thesis that the same proof applies to 2D, 3D, and people believed him. So, like Dirac and Heisenberg suggested another model of magnetism. Both of them did suggest. But then it took over, and it turned out that while there is no, at least as far as I know, I don't know any compound where magnetism is exactly Ising model. No, but ferroelectricity, yes, there are some crystals where it's exactly Ising model, but it still gives very good approximation, kind of grasps what is going on, and it has been used everywhere, from ecology to whatever, social networks, or even machine learning. I mean, the first way to train deep networks were Boltzmann machines, and this is basically based on statistical mechanical intuition. So for models, it's certainly true. Now, for theorems, for conjectures, I think we need these sort of conjectures like kind of a beacons. And you know, like I did complex analysis, I started doing it when Bieberbach conjecture was still open, that if you have a map of a disk into a complex plane and you write it as a series, you normalize, so it's z plus a z squared plus b z cubed, etc. Then that a is no more 2, 3, b no more than 3, and so on, that nth coefficient is no more than n. And it led to a lot of good research because people could grasp the question and then did something related. And in the end, when the branch solved it, partially killed the subject. You had the same effect with 3D topology after Perelman's intervention, that people invent a lot of things trying to do Poincare conjecture. So here, for example, it relates to your question. You asked that can you find always simple proof? There is a famous 4-color theorem that every planar map you can color in 4 colors. And as far as I know, last time I checked, there is only computer-assisted proof, which is not, let's say, entirely satisfactory. But the amount of research this problem led to, so for example, a few topologists, like famous ones like Den or Whitehead, they suggested in like 1904 and later approaches that let's count how many planar graphs you have with n vertices, some number. Let's count how many planar graphs with n vertices you can cover in 4 colors, another number. If the two numbers coincide, done. It was ultimately successful because people counted the number of planar graphs on the n vertices, they counted the number of coverings, but then there was this point you have raised, what about symmetries? So they could count it, but they couldn't factor out the symmetries. So they were always getting a bigger number because the symmetries were counted differently. But then it's basically like covering in 2 colors is like partition function of the Ising model. It's then 't Hooft had a proposition to do planar quantum gravity by doing random graphs. It's like Polyakov suggested taking the exponential of the Gaussian free field, which we have seen today, but it's very fruitful. In the sense that the fact that this theorem is proved kind of kills it as a source of inspiration. I'm sorry, but yeah, I think we need beacons. For this particular area, I can say what but enticed me to do it, that John Cardy, who was mentioned, so he made a group of 3 mathematicians and physicists, so it was Pujotsan, Nauban, and Langevins of Langevins program fame. They tried to suggest a program for making mathematics out of conformal field theory. And they studied the probability that there is a percolation connection joining the 2 opposite sides of rectangle, and numerically they conclude that there is a scaling limit, is independent of the lattice, and then they asked if it's independent of the lattice, then for every quadrangle shape there is a number. What is this number? And then Michael Eisenman told them, you know, there is this Belyan-Polyakov Zmolodchikov paper recent which says it should be conformally invariant. And they checked that it's really a function of conformal models. And then when John Cardy heard about it, he said, well, okay, I can write this function, I can write equation for it, it's a Riccati equation, so it's a hypergeometric function. And so when I was a student, there was this paper in Bulletin of IMS, so I wrote, okay, hypergeometric function, I like very much hypergeometric function, I'm a complex analyst, but trying to prove that something is hypergeometric function sounds intimidating. But a better complex analyst than me looked at it. It was Leonard Carlson, and he said that it was a hypergeometric function with coefficients 1/3, 2/3, 4/3, and coefficients there, they actually give map to a polygon, and these coefficients are slopes of the sides. So with slopes 1/3, 2/3, 4/3, it's an equilateral triangle. And so he observed that the cardinal form of equilateral triangle is just like linear on the bottom side. And then people said, well, that we can try to prove combinatorially without going into some deep things we don't understand, like Kac-Moody algebras or complex analysis. And many people like Schramm joined it, Carlson joined it, and I did because of this conjecture. It then turned out that we had to use some complicated stuff, and it was pure coincidence that it's linear for hexagonal, for a triangle. It had nothing to do with hexagonal lattice. It had to do with the mu I had being cube root of unity and nothing else. But the simple formulation really enticed many people to move in. So it's nice to have simple formulated problems.
Which leads to my next question. You told us that the Einstein for the aperiodic tiling was found by David Smith, who was a non-professional mathematician.
I've never met him, but my admiration goes to him. I really, it's really not, now I think, why didn't I look into that? I'm kind of, it's kind of, I'm jealous in a good sort of way. It's this theorem, it's one of my friends once said when he sees theorem like that, he thinks, Dennis Sullivan, that I must steal this theorem, it must be mine, it must be so nice to discover it.
Yeah.
But it's too late already, someone discovered it, so it's...
And then you told us he wrote to the Museum of Mathematics
That's,
in New York,
that's
and
what
they
people
tried
say.
to check the tiling with the software as a first thing. So this raises a couple of questions. The first is how much room do you think there is for non-professional mathematicians in this world, in the contemporary science? And the other one is, well, in part you already answered to this question. What do you think about asking the computer for help, so computer-assisted proofs and yes.
Well, the first one is, there is an unfortunate thing with all of science that we became rather more complicated than before, and there is this learning curve to join some areas. Some areas really you need to study a lot to join. Of course, we sort of simplify it because we make some constructs, like notion of continuity was very difficult 4 centuries ago. Now it's sort of, we use the symbol. Once you learn it, you just use it as one block without thinking about for every epsilon there is a delta. But it's, there are very, very few cases, yeah, I don't know. It's an interesting question. It's maybe the question I like more is, can one appreciate mathematics if one is not a mathematician? It's like, let's make an analogy. So suppose that you don't listen to music, but you just get the notes for the, I don't know, Mozart's 40th Symphony or Vivaldi, the Spring of Vivaldi, as being in Italy. So it's, if you don't know the note transcription, you don't realize that it's beautiful. I made this experiment once, giving a popular talk to kids, and 1/3 of the kids in the room, they were like 300, and 1/3 they were musicians. And I showed the Waltz of Flowers by Tchaikovsky, and like 1/3 said, oh, that's very beautiful. Well, yeah, but for me, I'm very bad with music, so it's for the sake of humanity, I don't play any instruments. But it's, well, I would enjoy it, but you wouldn't. But then mathematics is like that you need to do some training, so we see these notes, and when I appreciate, I have a few friends who are like well-known conductors or musicians, and then they really, conductors, it's even amazing because they hear immediately several voices, so math is like that. It's, you see e to the power 2 pi equal to 1, and it immediately conjures some images, so can we do it? You can imagine a world where people would sort of do math training only to enjoy this. I mean, like, in Italy, medieval ages, people like solved cubic equations for sport. At least that's what history books say. That, yeah, why so not? I have some friends who don't do mathematics, but who like to read popular literature, for example, or about science in general. But this contribution, yeah, it's rather rare, as is in other sciences, I think. But it's really amazing that it can happen. Yes. And the second question about artificial intelligence, well, I just went to a conference about it at the PFL Friday, was it this Friday or last Friday? I don't remember already. Well, time flies in non-linear way, but yeah, there was a guy who said that he wants to screw us all and write program which proves all the theorems. And apparently it was a famous guy. He was a famous guy who famous in machine learning, and I was not amused. Because it's like I like to spend time with my kids. I like listening to music. I like going to museums. I like doing mathematics. And he wants to kill this. And then he will invent a robot which will go to museums instead of me. So I don't know. It's a difficult question. It's a difficult question. I think that the things which I would certainly appreciate, I would appreciate a program which checks the proofs for mistakes, especially as an editor of journals. Now there are several programs which exist, like Coq and Lean. The only problem you need to rewrite the special language, which is like TeX or HTML. And just simple question. Suppose you have a paper which starts with let n be a natural number. Okay. You have to check the nationality of author to know what he means, or she. If he or she is French, it means 0, 1, 2, 3. If he or she is American, it means 1, 2, 3, 4. So there are like small things like that. In Italy, it starts with 1?
0.
I mean, French got it there. Actually, you know, French, it was starting with 1 according to ANSI standards up to 2008, and then it started with 0. So it's you know, it's even time dependent. Like you know, ANSI standards, it's okay, well, yeah, so okay, Italians and French and Russian and Americans are now on different sides of this divide. Well, okay, yeah. So these programs, it would be nice, but it would be nice that there is a computer program which formalizes all existing texts. So this is one thing. The other thing is like search of information. Already MassSciNet was a big step. Because when I was writing master thesis, I was using these sort of cards to do bibliography. And Google Scholar is a big step. But I would appreciate something which would find links better and reasonable things better. And some people say that things which formulates conjecture or checks conjecture, so you say that I think that a random tiling of a whatever hexagon has this Arctic circle. Can you try bigger examples that would run programs and return with answer? I think that I also appreciate, so it would be reachable. But the thing which proves theorems instead of us, I mean, we have fun proving theorems. I mean, it's not only how we earn our salary, but it's like if you have a program which draws paintings instead of Picasso or Modigliani or Da Vinci, I mean, yeah, I'm not sure. I would appreciate that. But I mean, something like that is coming. It's really, and it's unpredictable. Well, as ChatGPT-4 has shown us, it comes from unexpected directions. So it's...
Bruno.
To check the proof. Check the proof, there are programs, but you have to write it in a special language. So now, if ChatGPT-4 would be able to convert my proofs into this special language, that would be nice. But I think eventually it will be there. But it's a fascinating thing for a different discussion, and but people are totally lost, especially people in the area. They're kind of in the fog of what's going to happen.
Yes, perhaps just one last question. So, as you showed us, you live at the edge between mathematics and physics.
But on the mathematical side.
Okay. Yes, because you work for a mathematics department,
because
right?
I don't have a LaTeX style file for physics review letters. That's the reason.
Yeah. So, in Cardy's words, when he wrote an article on the occasion of your Fields Medal.
Oh, he did?
He did. He explicitly mentions you and your work as a striking example of cross-fertilization between physics and mathematics. So the question is, how often does this happen? Is it a rarity or not? How difficult is it? And do you think that there is something like lost in translation between the two communities?
Well, I think it happens much more often than we think, but much less often than I would like to. So like Tullio Levi-Civita was mentioned, and certainly back then, regarding relativity, like Einstein, for example, what Tullio taught Albert Einstein to do is to write everything without coordinates, which Einstein's training didn't allow him to, and which basically wasn't that important for special relativity, but which was cornerstone of general relativity. But Einstein was a smart guy, he knew whom to ask, and he liked spaghetti. Yeah, that's, and playing violin. But it's sort of, if you look at quantum physics, if you look at the Solvay conferences 100 years ago, you would see people like Hilbert and, well, many other mathematicians. So they were in parallel developing math tools, and like Hilbert spaces were developed for different purposes, but suddenly came very handy for quantum mechanics. But then it sort of came back with like Fock spaces and different other things which can be used in mathematics. Like string theory is a prime example. So far it was sort of, its impact on mathematics was bigger than on, let's say, physics in a sense. But it's, no, it's good, Marcus. Yeah, that's okay, get a chocolate and shut up. Yeah, that's yeah, so it's, no, it's interesting. It could be very well that what is missing is some piece of mathematics which already exists and physicists don't know. It can very well be that. And it's, well, we had basically this collaboration. It started with Newton and Kepler, and when there was a lot of, finally there were precise enough measurements to formulate good conjectures, which sort of seemed astonishingly interesting for mathematicians, like this sort of elliptic orbits. And we still have this collaboration, but yeah, so it's, yeah, I think there will be more of it. What's more interesting, whether there will be such collaboration of mathematicians with biologists. And there will be, the answer is yes.
Okay, so perhaps one last thought about what would you recommend to young researchers?
I mean, what to study or how to study?
Both.
No, but how try different things and read a lot of things, because it's you have much more free time when you are a grad student or postdoc. It's you know, now they write a lot that it's like in Switzerland it's a big thing, that precarity of positions of young researchers, they don't have a permanent job. Of course there is this, and especially hard if you have a family, but on the other hand I kind of remember that I had this side to my career, and I thought that if I don't find a good job I will leave for the industry, and then I get the job. But on the other hand, I learned so much stuff, so in a sense I had more time to do mathematics back then than now. So it's, in a sense, it was nice. So just read a lot, talk to people a lot, go to as many seminars as you can, even if you don't understand everything you learn by osmosis, and listen for good open problems. It's often the best problems you solve are not the ones your advisor gives to you, but the ones you hear in some seminar. Because it's you know, it's like there is this saying from Russian playwright of 19th century that some people like watermelon and some like lardo di Toscana, whatever Russian analog. So some people like the pig fat, and some people like watermelon. So you never know in advance what kind of science you would like and what kind will work for you. So just try as many things. As for the area, I think it's certainly fabulous times for mathematics. There are so many exciting things. I think it's better time than 30 years ago. It's more a time of synthesis when areas come together. Now, in relation to physics, it's well, I think it's good. Like it's good, very good time for mathematical physics too, for several areas. I think it will be. As far as I remember, people say that the age of mathematical biology is coming, and they say it's like coming next year, for us 40 years, so it's actually now coming. So actually my last 3 papers are in biology, so it's, well, okay, out of my last 5 papers, 3 are in biology, and I hope the next 3 ones too, but they finally have this data like Kepler, data of Tycho-Brahe, which Kepler analyzed, so they're now missing Kepler to analyze the data and Newton to make sense of it. But this is not something you have now in high-energy physics, and something you won't have in high-energy physics. We won't have in high-energy physics, unfortunately, for a couple of decades. That they have really treasure trove of data which being produced but not analyzed. So it's, but it's not that I'm advising everyone to move there, but it's very good to look at it from a perspective of theoretical physicist or mathematician, better yet theoretical physicist, because they used to have this sort of fuzzy approach because they didn't have good data. Now they have good data. And it's on several fronts. There are like many advanced in engineering biology. It's not only genetics, it's everything, like from microscopy to genetical engineering. So it's, for example, like they're getting for some small animals, like zebrafish, you can do the complete neural recording of their brain. Okay, analyze, try to understand how the zebrafish thinks. And half of this is actually available for free on the web, because usually it's done with collaborations which have to put it on the web, so you can just go and analyze. But it's a lot of data, obviously. If it's 100K neurons and over 10 minutes, it's yeah.
Okay, thank you very much for the insight.
Oh, thank you.
Okay, yes.
Thank you. Just a final announcement for those of you who are in the room, who are here. There will be an opportunity to have a group picture taken outside on the lawn, just outside the auditorium. And after the group picture, there will be colleagues helping direct you to the exit, which is the same way you entered the auditorium. Just a polite request not to linger for too long inside the garden after the event. Well, thank you all again. Thank you, Professor Smirnov, and a very good evening to you all. Bye-bye.
Of chocolates.